Hello, and welcome to Space Historians, where big questions unfold gently enough to rest beside. Tonight, before you drift into the soft rhythm of sleep, I'd like to invite you somewhere strange, not far in the way we usually think of distance, but outward, past the comfortable edges of what we know, past the moon, past the planets, past even the farthest stars you can see, out to a place where the very idea of place begins to dissolve, out to where we ask a question that sounds simple but stretches into something vast and beautiful. How do we know where the universe ends? It's the kind of question that feels like it should have an answer, something definite, a boundary we could point to and say, there, that's where everything stops. But the universe, in its quiet way, doesn't make things so easy. The more we look, the more we find. The farther we reach, the more space opens up before us. It's as if the cosmos refuses to be contained, refuses to give us the satisfaction of an edge. Before we begin this gentle exploration, I wonder where you are right now. Maybe you're lying in bed with the lights low, the day finally settling into stillness. Maybe you're watching the night through a window, seeing a few stars pierce through the glow of streetlights. Wherever you are, whatever your small corner of the world looks like tonight, you're standing inside the very mystery we're about to explore. The universe doesn't end somewhere far away. It surrounds you completely, even now. If this kind of wondering helps you unwind, if cosmic questions wrapped in calm narration ease your mind before rest, I'd be grateful if you gave this a like or subscribed. It helps this little space of curiosity and peace find others who might need it too. And for those already here, thank you. You're part of this voyage through the dark, so take a breath, let it out slowly. Let the concerns of the day drift away like clouds. Tonight, we're not rushing anywhere. We're simply following a question into the vastness, letting it unfold at its own pace. You don't need to understand everything. You don't even need to stay awake. Just listen and let the universe reveal itself, one gentle thought at a time. The question of where the universe ends is really a question about boundaries, about edges, about the human need to know where things stop. But what if the universe doesn't stop? What if it simply continues, forever, in all directions? Or what if it curves back on itself, so that travelling far enough in one direction brings you home again, like walking around the surface of Earth? These aren't just philosophical puzzles. They're questions we can explore, questions with clues hidden in light and distance and time. And tonight, we'll follow those clues together, moving slowly through the evidence, through the wonder, through the quiet realization that the universe might be far stranger and more beautiful than any boundary we could imagine. The cosmos is waiting. Let's begin. There's something almost instinctive about wanting to know where things end. We're creatures of edges, of boundaries, of clear divisions between here and there. A room has walls, a field has fences, an ocean meets a shore. Even the Earth itself, vast as it is, has limits you can measure. If you travelled far enough in any direction, eventually you'd find yourself back where you started, having circled the globe. It's finite, contained, knowable. But the universe doesn't work that way. And the moment we realised that, everything changed. For most of human history, the cosmos seemed manageable. The sky was a dome, the stars fixed points of light, the heavens a ceiling we could see but never touch. Ancient peoples imagined edges everywhere. The Greeks pictured crystalline spheres surrounding Earth. Medieval thinkers placed heaven beyond the outermost shell. Even when we learned the Earth was round, when we understood the sun sat at the centre of our solar system, we still carried the assumption that somewhere, somehow, there must be a boundary. a place where creation stopped and nothing began. Then came the telescopes, better glass, sharper lenses, more sensitive instruments, and with each improvement, the edge moved farther away. The Milky Way turned out to be a galaxy among billions. Those billions stretched across distances measured not in miles or even light years, but in millions and billions of light years. And still, nowhere did we find a wall. Nowhere did space simply stop. Instead, it kept going, revealing more galaxies, more structures, more vastness than anyone had imagined possible. The impossible beginning of our modern understanding arrived in the early 20th century, when astronomers noticed something strange. The light from distant galaxies was shifted toward the red end of the spectrum, not just a few galaxies, but nearly all of them. And the farther away they were, the more their light was stretched. At first, no one understood what this meant. But slowly, carefully, the evidence assembled itself into a revelation that would reshape everything we thought we knew about existence itself. The universe was expanding, not into something, not through some pre-existing space, but expanding in itself. Every point in space was moving away from every other point, like dots drawn on the surface of an inflating balloon. The fabric of reality was stretching, carrying galaxies apart, growing larger with every passing moment. And if the universe was expanding now, that meant it must have been smaller in the past. Wind the clock backward far enough, and you arrive at a moment when everything, all of space and time and matter and energy, was compressed into something unimaginably small and dense. That moment, that beginning, we now call the Big Bang. But even that name is misleading. It wasn't an explosion in space. It was the expansion of space itself. There was no outside for it to explode into. There was no before in the usual sense, because time itself began with that expansion. Every direction you can point contains the remnant of that origin. Every piece of the universe emerged from the same initial state. This discovery didn't just change astronomy, it changed the very question we're asking tonight. Because if the universe began as something finite and has been expanding ever since, where does it end now? Does it have an edge somewhere out there, a boundary beyond which nothing exists? Or does it go on forever, infinite in extent, even though it had a finite beginning? The answer, as we've slowly discovered, is stranger than either of those options. The universe might not have an edge at all, not in the way we imagine edges. It might be both finite and boundless, like the surface of a sphere. Or it might be infinite, stretching endlessly in all directions, with no center and no boundary. Both possibilities fit within the laws of physics. Both are consistent with what we observe. But here's where it gets truly remarkable. We can never see the entire universe, no matter which of those possibilities is true. We can only see as far as light has been able to travel since the beginning. That distance, that cosmic horizon, marks the edge of the observable universe. It's about 46 billion light years in every direction, creating a sphere around us about 93 billion light years across. But that's not the edge of the universe itself. It's just the edge of what we can see. Beyond that horizon, space continues. Galaxies exist that we'll never observe. They're light forever unable to reach us, because the expansion of space carries them away faster than their light can travel toward us. In a very real sense, there are parts of the universe that are forever beyond our knowledge, not because they're hidden, but because the structure of space-time itself prevents their light from ever arriving. This is the impossible beginning of understanding where the universe ends. It doesn't end in space, it ends in time. It ends at the limit of observation, at the horizon drawn by light's finite speed, and the universe's finite age. The edge we can measure isn't a wall at the boundary of existence. It's a line separating what can be known from what must remain forever unknown. Think about that for a moment. The universe doesn't stop at some distant location. It stops at a distance defined by how long light has had to travel. Every galaxy we see is a message from the past. A photon that began its journey billions of years ago and only now completes it by entering our telescopes. The farther away we look, the further back in time we see. The edge of the observable universe is really the edge of observable time. The moment when the universe was young enough, hot enough, opaque enough that light couldn't yet travel freely. That edge is called the cosmic microwave background. It's the oldest light we can ever see, the afterglow of the moment when the universe cooled enough for atoms to form and photons to break free. Before that moment, space was filled with a glowing fog, light constantly scattering off charged particles. But when electrons and protons combined into neutral hydrogen, the fog cleared, light was released, and it's been travelling ever since, stretched by billions of years of cosmic expansion into faint microwave radiation that fills the entire sky. So when we ask where the universe ends, we're really asking two different questions. Where does space end, if anywhere? And where does our ability to see space end? The first question remains open, possibly unanswerable. The second question has a definite answer. Our vision ends at the cosmic microwave background, at the surface of last scattering, at the moment roughly 380,000 years after the Big Bang when the universe became transparent. Beyond that light, the universe continues, but we'll never see it. Not with telescopes that detect electromagnetic radiation. We're surrounded by a sphere of visibility, and everything beyond that sphere might as well be in another realm entirely. It exists, presumably following the same laws of physics, containing galaxies and stars, and perhaps even life. But we'll never know for certain. The information can't reach us. The cosmic horizon is absolute. This realization is both humbling and strangely beautiful. We live inside a bubble of light, surrounded by history made visible. Every direction we look shows us the universe at a different age, with nearby objects appearing as they were recently, and distant objects appearing as they were billions of years ago. The night sky isn't a snapshot of now. It's a layered painting of then, with each layer representing a different moment in cosmic time. And somewhere beyond all those layers, beyond the farthest light we'll ever detect, the universe continues its quiet existence, expanding, evolving, changing in ways we'll never witness. That unknown expanse might be 10 times larger than what we can see. It might be 1,000 times larger. It might be infinite. We'll never know. The edge of the universe, if it exists, lies forever beyond the edge of observation. So the impossible beginning of this story is really a beginning of understanding that some questions have no final answers. That the universe is too vast, too old, too distant for us to ever see it whole. We're like people standing on an endless plain surrounded by fog, able to see a certain distance in every direction but never able to know what lies beyond the mist. It's temporal. It's the limit imposed by light's finite speed and the universe's finite age. And yet, even within that limit, even within that cosmic bubble we call the observable universe, there's more than enough to fill every lifetime with wonder. Trillions of galaxies, each containing billions of stars, each star potentially surrounded by planets, each planet a world unto itself. The visible universe is so vast that, even if we could never see beyond it, we'd still be surrounded by more space, more time, more structure than we could ever fully explore. The edge of the universe, then, isn't a place we can travel to or a boundary we can measure directly. It's a concept, a limit defined by physics and observation. It's the point where knowing gives way to imagining, where evidence fades into speculation, where science meets philosophy. And in that meeting place, in that impossible space between the known and the unknowable, we find ourselves tonight asking a question that has no simple answer but endless fascinating implications. The universe might end somewhere, or it might not, but our view of it definitely ends, and that ending is something we can study, measure, and understand. So that's where we'll begin our journey. Not at the edge of everything, but at the edge of what can be seen. From there, we'll work our way outward, following the evidence, tracing the boundaries of knowledge, and discovering what it means to exist in a cosmos that might have no edge at all. There's a mountain in California where the air is thin and the stars shine with unusual clarity. Mount Wilson rises above the haze of Los Angeles, high enough that the city lights fade into insignificance and the night sky opens like a book. In the early decades of the 20th century, this mountain became the stage for one of humanity's greatest revelations, not because of what was on the mountain, but because of what could be seen from it. The Hooker telescope sat in its dome like a giant eye pointed toward the heavens. At the time of its completion in 1913, it was the largest telescope in the world, its mirror 100 inches across, capable of gathering more light than any instrument before it. Astronomers came from around the world to use it, spending cold nights at the eyepiece, guiding the massive instrument across the sky, capturing faint glimmers of light on photographic plates that would later be developed and studied in detail. The mountain was quiet at night, far from the noise of civilization. The only sounds were the gentle hum of the telescope's mechanisms and the occasional rustle of wind through the pine trees. Up there, surrounded by darkness and starlight, it was easy to feel the weight of the cosmos pressing down, the vast distances made somehow more real by the clarity of the view. The Milky Way stretched overhead like a river of light, and scattered among it were faint smudges that telescopes revealed to be something more. Structures with their own shapes and patterns. These nebulae, as they were called, had puzzled astronomers for generations. Some were clearly clouds of gas within our own galaxy, glowing regions where new stars were being born. But others looked different. They had spiral shapes, distinct cores, arms that curved outward in graceful arcs. They looked, in fact, like miniature galaxies themselves. But were they, or were they, simply unusual formations within the Milky Way? The question divided the astronomical community. Some argued that these spiral nebulae were island universes, separate galaxies far beyond our own. Others insisted they were part of the Milky Way, perhaps smaller systems orbiting within it. The debate became known as the Great Debate, and in 1920, two prominent astronomers faced off in a formal discussion of the issue. Harlow Shapley argued that the Milky Way was vast and that the spiral nebulae were contained within it. Heber Curtis argued that they were external galaxies, each comparable in size to our own. Neither man had definitive proof. The distances were too great to measure directly, and without knowing how far away the nebulae were, it was impossible to determine their true size. A small object nearby could look identical to a large object far away. The telescope could reveal shape and brightness, but not distance. That required something else, some cosmic measuring, stick that could reach across the void. Into this setting came a young astronomer named Edwin Hubble. He wasn't the first to study the nebulae, and he wasn't working alone, but he had access to the Hooker telescope and the patience to use it night after night, capturing images of the Andromeda Nebula, the brightest and largest of the spiral nebulae visible from Earth. He was looking for something specific, a type of star whose behavior could reveal its distance. These stars were called Cepheid variables, and they had a remarkable property. They pulsed, brightening and dimming in a regular cycle, and the period of that cycle was directly related to their true brightness. A Cepheid that pulsed slowly was intrinsically brighter than one that pulsed quickly. This relationship had been discovered years earlier by Henrietta Leavitt, a woman working as a computer at Harvard Observatory, analysing thousands of photographic plates and noticing patterns that others had missed. Hubble knew that, if he could find Cepheid variables in the Andromeda Nebula, he could measure their periods, calculate their true brightness, compare that to how bright they appeared from Earth, and thereby determine their distance. It was elegant in principle, but difficult in practice. The stars in Andromeda were faint, requiring long exposures and careful measurement. But Hubble was persistent. He took image after image, comparing them, looking for stars that changed brightness in the characteristic pattern of Cepheids, and he found them. In 1923, he identified a Cepheid variable in Andromeda and measured its period. The calculations that followed were straightforward but stunning in their implications. The star was far away, very far away, so far that Andromeda could not possibly be part of the Milky Way. It was an entirely separate galaxy, over 2 million light-years distant, a vast collection of stars comparable to our own, but separated by an almost incomprehensible void. The Mesa setting for this discovery was humble. A telescope on a mountain, a patient observer, a photographic plate capturing light that had travelled for millions of years. There was no grand announcement, no sudden revelation. Hubble simply did the work, made the measurements, and published the results. But those results changed everything. If Andromeda was a separate galaxy, then so were all the other spiral nebulae. The universe wasn't a single structure. It was a vast expanse filled with galaxies, each one an island of stars drifting in the cosmic ocean. The mountain where this happened is still there. The Hooker telescope still stands in its dome, though newer and larger instruments have long since surpassed it. But the work done there in those early years remains foundational. It was the place where humanity first truly glimpsed the scale of the universe, where we learned that our home galaxy was just one among countless others, where the question of where the universe ends became suddenly more complex and more profound. The setting matters because it reminds us that great discoveries often come from quiet places. There was no fanfare, no ceremony, just careful observation and patient calculation. The universe revealed itself not through revelation but through evidence, one photon at a time, accumulated over cold nights on a mountain far from the comforts of civilization. Hubble and others like him spent years of their lives pursuing these measurements, driven by curiosity and the desire to know. And what they found set the stage for everything that would follow. Because once we knew there were other galaxies, once we understood the scale of the cosmos, the question of where it ends became urgent. If galaxies stretched in all directions, was there a limit? Did they go on forever? Or was there a boundary somewhere, a place where space simply stopped? The mountain couldn't answer that question, but it gave us the tools to begin asking it properly. The Hooker telescope showed us that the universe was larger than we'd imagined, but it also showed us something subtler. It demonstrated that the universe could be measured, that distances which seemed impossible to determine could be calculated through careful observation and clever reasoning. We couldn't travel to Andromeda, couldn't visit those distant stars, but we could still know how far away they were. Light itself became our messenger, and in its patterns we could read the story of cosmic distance. This was the true beginning of modern cosmology, the study of the universe as a whole. Before Hubble's measurements, astronomers studied individual objects, stars and planets and nebulae. After, they began to think in terms of cosmic structure, the distribution of galaxies across space, the relationship between distance and time. The universe became something that could be mapped, modelled, and understood in mathematical terms. The setting also reminds us of the role of technology in expanding knowledge. Without the Hooker telescope, Hubble couldn't have seen the Cepheid variables in Andromeda. They were simply too faint for smaller instruments. Every advance in telescope technology has pushed the boundary of the observable universe outward, revealing more galaxies, more structure, more distance. The tools we build determine what we can see, and what we can see shapes what we can understand. But the mountain setting also carries a certain poetry. Up there, removed from daily life, surrounded by darkness and silence, the cosmos feels closer somehow. The stars aren't abstract points of light, but real objects, distant suns with their own stories. The sense of scale becomes visceral. You can feel the vastness, even if you can't quite comprehend it. That feeling, that mixture of awe and curiosity, is what drove the astronomers who work there and continues to drive those who study the universe today. Mount Wilson was where we first learned to measure the unmeasurable, to find distances to objects so far away that their light takes millions of years to reach us. It was where we discovered that the Milky Way, once thought to be the entire universe, was just one galaxy among many. And it was where we began to ask, seriously and scientifically, where does it all end? How far does space extend? Is there a limit, or does it go on forever? The answers to those questions would take decades to emerge, requiring newer telescopes, more sophisticated observations, and theoretical breakthroughs that no one on Mount Wilson could have anticipated. But the foundation was laid there, on that mountain, in those cold nights spent staring at faint points of light. The setting gave us the first real glimpse of cosmic scale, and with that glimpse came a question that would define cosmology for generations. Where does the universe end? The mountain couldn't tell us, but it showed us how to begin looking for an answer. And in that beginning, in that patient accumulation of evidence, we found not just knowledge, but wonder. The universe was larger than we'd thought, stranger than we'd imagined, and far more beautiful than any boundary could contain. The light arrives silently, one photon at a time, carrying information encoded in its wavelength. When astronomers in the 1920s began analyzing light from distant galaxies, they noticed something peculiar. The spectrum, the rainbow of colors that results from splitting light into its component wavelengths, looked wrong. Not dramatically wrong, but subtly shifted. The pattern of dark lines that identify specific elements, hydrogen, helium, calcium, were all present, but they weren't quite where they should be. The lines were shifted toward the red end of the spectrum. Every line, every element, every measurable feature of the light had been stretched to longer wavelengths. It was as if the light itself had been pulled, extended, changed during its long journey across space. At first, astronomers weren't sure what this meant. Light could be redshifted by motion, by the Doppler effect, the same phenomenon that makes a train whistle change pitch as it passes. But the amount of redshift they were measuring suggested velocities that seemed impossibly high. Edwin Hubble, who had already revolutionized astronomy by measuring the distance to Andromeda, turned his attention to this mystery. He had access to distance measurements for many galaxies now, thanks to Cepheid variables and other techniques, and he also had access to spectroscopic measurements showing the redshift of those galaxies. When he plotted one against the other, distance against velocity, a pattern emerged. The farther away a galaxy was, the faster it appeared to be moving away from us. It wasn't random, it was systematic. Nearby galaxies showed small redshifts, modest velocities. Distant galaxies showed larger redshifts, higher velocities. The relationship was linear, double the distance, and the velocity doubled as, well. It was a pattern so clear, so undeniable, that it demanded an explanation. Hubble published his findings in 1929, and they changed everything. The discovery was simple to state, but profound in its implications. The universe was expanding, not just in one direction, not just in our local region of space, but everywhere, uniformly, in all directions at once. Space itself was stretching, carrying galaxies apart like dots drawn on the surface of an inflating balloon. This was the spark of mystery that would ignite decades of cosmological revolution. Because if the universe was expanding now, it must have been smaller in the past. And if you traced that expansion backward, following the galaxies as they converged, you arrived at a moment when all of space was compressed into something infinitesimally small. A beginning. A moment of creation. The idea was radical. For centuries, scientists and philosophers had assumed the universe was eternal and unchanging. Galaxies might move, stars might be born and die, but the overall structure of space and time was thought to be static. Hubble's discovery shattered that assumption. The universe had a history. It evolved. It changed. And it had, apparently, a definite starting point. Not everyone accepted this immediately. Some astronomers resisted the idea of a cosmic beginning, finding it too close to religious creation myths for comfort. Others proposed alternative explanations for the redshift, suggesting that light might lose energy over vast distances, a tired light hypothesis that could mimic the appearance of expansion without requiring the universe to actually grow. But as more evidence accumulated, as more galaxies were measured and more patterns confirmed, the expansion became undeniable. The spark of mystery lay not just in the fact of expansion, but in what it implied about the nature of space itself. If the universe was expanding, then space wasn't a passive stage on which events unfolded. It was an active participant, a dynamic entity that could stretch, bend, and evolve. This fit beautifully with Einstein's theory of general relativity, which had predicted just such behavior. Einstein's equations described how matter and energy curve space-time, and they naturally allowed for solutions where the universe expanded or contracted. Ironically, Einstein himself had initially rejected this possibility. When he first formulated general relativity in 1915, he assumed the universe was static and added a term to his equations, the cosmological constant, to prevent expansion or contraction. When Hubble's observations showed that the universe was indeed expanding, Einstein reportedly called the cosmological constant his greatest blunder. The universe didn't need to be held static. Its natural state was motion, growth, change. The discovery of cosmic expansion transformed the question of where the universe ends. If space was expanding, carrying galaxies apart, then, in principle, it could expand forever. There might be no edge, in the traditional sense, no boundary where space stopped. Instead, the universe could be infinite, with galaxies stretching endlessly in all directions, all moving away from each other as space itself grew larger. But expansion also introduced a new kind of edge, a temporal one. If the universe had been expanding for a finite amount of time, then there was a limit to how far we could see. Light travels at a fixed speed, and it's been travelling for only as long as the universe has existed. That means there's a horizon, a distance beyond which light hasn't had time to reach us yet. The universe might continue beyond that horizon, but we'd never be able to observe it. The spark of mystery also ignited questions about the ultimate fate of the cosmos. If the universe was expanding, would it expand forever? Or would gravity eventually slow the expansion, halt it, and reverse it, causing the universe to collapse back on itself? The answer depended on how much matter the universe contained. If there was enough mass, its gravity would eventually overcome the expansion. If there wasn't, the universe would grow forever, thinning and cooling until it became a cold, dark, empty expanse. Hubble's discovery didn't answer these questions, but it gave us the framework to ask them properly. It transformed cosmology from a philosophical discipline into an observational science. We could measure the rate of expansion. We could calculate how long the universe had been growing. We could estimate its age, trace its history, and make predictions about its future. The linear relationship between distance and velocity, now known as Hubble's law, became one of the fundamental tools of astronomy. By measuring the redshift of a galaxy, astronomers could determine how far away it was. The more the light was stretched, the greater the distance. This turned every galaxy into a signpost, a marker indicating its position in space and time. The universe became mappable in a way it never had been before. But the mystery deepened even as it clarified. The expansion seemed to be the same in all directions. No matter which way we looked, galaxies were moving away from us. This created an illusion of centrality, as if we were at the center of the expansion. But the mathematics showed that this was just a consequence of the expansion itself. From any galaxy's perspective, every other galaxy would appear to be moving away. There was no center. Every point in the universe was equivalent. This uniformity suggested something profound about the universe's structure. It wasn't just expanding. It was expanding uniformly, homogeneously, the same way everywhere. On the largest scales, the universe looked the same in all directions. This principle, called isotropy, combined with the assumption that the universe looks the same from every vantage point, called homogeneity, became cornerstones of modern cosmology. The universe had a structure, a pattern, a form that could be described mathematically. The spark of mystery that Hubble ignited continues to burn today. We now know that the expansion is accelerating, driven by something called dark energy that makes up nearly 70% of the universe's content. We know the universe is about 13.8 billion years old. We know the observable universe extends about 46 billion light years in every direction, but we still don't know if the universe is infinite or finite, whether it has an edge or curves back on itself, whether it will expand forever or eventually end in some other way. The discovery of cosmic expansion was the moment when the question of where the universe ends became a scientific question rather than a philosophical one. It gave us tools, methods, evidence. It showed us that the universe has a history, a trajectory, a story that can be traced through careful observation and measurement. And it reminded us that the cosmos is far stranger and more dynamic than we ever imagined. The light that reaches us from distant galaxies carries that story. Each photon has been traveling for millions or billions of years, stretched by the expansion of space, arriving redshifted and faint, but still carrying information about the universe's past. When we collect that light, when we analyze its spectrum and measure its shift, we're reading a message written in the language of physics. A message that tells us the universe is not static but growing, not eternal but evolving, not simple but endlessly complex. And that spark, that moment of realization when Hubble saw the pattern in his data and understood what it meant, remains one of the pivotal moments in human history. It was the instant when we discovered that the universe has a story, that it began somewhere and is going somewhere, that it's not a fixed stage but a dynamic process. The question of where it ends became, in that moment, a question we could actually pursue, following the evidence wherever it led, trusting that the universe would reveal its secrets if only we learned how to look. When the news began to spread through the scientific community that the universe was expanding, the response was not uniform. Some astronomers embraced the finding immediately, recognizing it as the missing piece in a cosmic puzzle they'd been trying to solve. Others resisted, uncomfortable with the implications, reluctant to abandon the comfortable assumption of an eternal, unchanging cosmos. The reaction was deeply human, a mixture of excitement and skepticism, wonder and doubt. For those who accepted the evidence, the implications were staggering. If the universe was expanding, growing larger with every passing moment, then it must have been smaller in the past. Follow that logic to its conclusion, and you arrived at a beginning, a moment when everything emerged from a state of unimaginable density and temperature. The universe, it seemed, had been born. And if it had been born, then it could also die, could end in some distant future when the expansion finally ran its course. This idea of cosmic birth contradicted centuries of philosophical and scientific thinking. Aristotle had argued that the universe was eternal, without beginning or end. Many religions had creation myths, but those were matters of faith, not science. The notion that scientific observation could point to an actual moment of creation felt revolutionary and unsettling in equal measure. It blurred the line between physics and metaphysics, between what could be measured and what could only be imagined. Some of the resistance came from scientific caution. The measurements weren't perfect. The distances to galaxies were uncertain, based on techniques that involved multiple steps and assumptions. The redshifts could potentially be explained by other phenomena. Perhaps light lost energy over vast distances in ways we didn't understand. Perhaps the universe wasn't actually expanding, but something else was causing the redshift pattern. Good scientists questioned everything, and the expansion of the universe was no exception. But as more data accumulated, as more galaxies were measured and more patterns confirmed, the skeptics found themselves with fewer and fewer alternatives. The expansion wasn't an artifact of bad measurements or misinterpreted data. It was real. The universe was growing, and no amount of disbelief could change that fact. The evidence, as it so often does in science, gradually overwhelmed the resistance. For the public, the response was filtered through newspaper articles and popular lectures, often simplified to the point of distortion. Headlines announced that the universe was flying apart, that galaxies were rushing away from Earth at incredible speeds. Some articles suggested that the expansion meant the universe would eventually tear itself to pieces. Others wondered if the beginning implied a creator, bringing religious debates into scientific discussions in ways that made many astronomers uncomfortable. But among those who truly understood what the expansion meant, the response was awe, not just at the fact itself, but at what it revealed about the universe's nature. Space itself was dynamic, flexible, capable of growth and change. Time and space were interwoven, part of a single fabric that responded to the presence of matter and energy. The universe wasn't a container holding things. It was an evolving structure, a process unfolding according to mathematical laws. This realization changed how scientists thought about cosmology. Before the discovery of expansion, astronomy was largely descriptive. You observed celestial objects, catalogued them, measured their properties, but there was no overarching theory of how the universe as a whole worked. After the discovery, cosmology became a science of evolution and dynamics. You could ask questions about the universe's past and future. You could make predictions about what you'd see at different distances, corresponding to different times in cosmic history. The awe extended to the mathematical elegance of it all. Einstein's equations, formulated more than a decade before Hubble's observations, naturally allowed for an expanding universe. The mathematics had predicted the possibility before the observations confirmed it. This suggested that the equations captured something deep and true about reality, that the language of mathematics could describe cosmic behavior in ways that transcended human intuition. Some scientists found comfort in this. If the universe followed mathematical laws, then it was comprehensible, potentially knowable in its entirety. Others found it mysterious. Why should the universe follow mathematical laws at all? Why should human minds, evolved to survive on one small planet, be capable of understanding the cosmos on its largest scales? The expansion of the universe answered many questions, but raised new ones about the relationship between mind and cosmos, between observer and observed. There was also a kind of existential response, harder to quantify but deeply felt. The expanding universe meant that our cosmic address had changed. We weren't just on a planet orbiting a star in a galaxy. We were in a dynamic, evolving universe that was racing outward, carrying us along with it. The ground beneath our feet, metaphorically speaking, wasn't solid. It was expanding, stretching, growing. We were passengers on a cosmic journey that began billions of years ago and would continue for billions more. This perspective shift affected how people thought about time. If the universe had a beginning, then time itself had a beginning. There was no before the Big Bang, or if there was, it was fundamentally inaccessible to science. Time was not an infinite backdrop against which events occurred. It was part of the story itself, emerging along with space and matter from some initial condition we could barely imagine. The disbelief, where it persisted, often came from an inability to let go of old certainties. The eternal universe was comforting in its own way. It required no explanation for its existence. It simply was, always had been, always would be. An expanding universe demanded an explanation. Why did it begin? What caused the expansion? What would happen when it ended, if it ended? These questions had no easy answers, and some preferred the certainty of eternal existence to the uncertainty of cosmic evolution. But the evidence didn't care about comfort or preference. The galaxies were redshifted, the farther ones more so than the nearer ones. The pattern was consistent, measurable, repeatable. Other observatories confirmed Hubble's findings. Astronomers around the world saw the same thing. The universe was expanding, and no amount of disbelief could make it stop. There was also wonder at the sheer audacity of the claim. Human beings, living for decades on a small planet, had somehow discovered a truth about the entire cosmos. We had measured the expansion of space itself, traced it back to a beginning, and calculated the age of everything. The scale of the achievement was matched only by the scale of what had been discovered. It was a moment of profound connection between the very small and the very large, between finite minds and infinite space. The response among cosmologists shifted from awe to urgency. If the universe was expanding, then understanding that expansion became the central problem of cosmology. What was driving it? Would it continue forever? Was the rate of expansion changing over time? These questions required new observations, new telescopes, new techniques for measuring distances and velocities across cosmic scales. The discovery sparked a research program that continues to this day. Some of the awe came from recognizing that we were witnessing the universe in a specific phase of its evolution. The expansion meant that the cosmos looked different now than it did in the past, and would look different in the future. We happened to exist at a moment when stars still shone, when galaxies were still forming, when the expansion was neither too fast nor too slow. It was a privileged moment in cosmic history, and we were alive to see it. The disbelief faded as the generations changed. Those who had grown up assuming an eternal universe eventually gave way to those who learned about cosmic expansion from the beginning. The expanding universe became not a controversial claim but an established fact, the foundation on which all modern cosmology was built. The awe remained, though, tempered by familiarity, but never fully extinguished. Because the truth is, an expanding universe should never stop being astonishing. The fact that we can detect it, measure it, trace its history, and predict its future is remarkable. Not because galaxies are moving, but because the fabric of reality is stretching, defies everyday intuition. We live in a universe that doesn't stand still, and that realization, once it truly sinks in, changes everything. The first response to the discovery of cosmic expansion was a mixture of awe and disbelief, acceptance and resistance, wonder and confusion. It was the human reaction to a truth too large to grasp all at once, a revelation that required both the data and the imagination to comprehend. And in that response, in that struggle to accept what the evidence showed, we see something essential about how science works. Not as a collection of facts handed down from authority, but as a process of discovery, debate, and gradual understanding built from evidence and reason. There's an inherent tension in trying to understand where the universe ends. On one hand, science demands precision, measurement, testable predictions. On the other hand, the universe presents us with phenomena that resist easy measurement, concepts that strain the limits of language and thought. The contradiction isn't a failure of either science or mystery. It's the natural consequence of finite beings trying to comprehend something potentially infinite. The scientific method works beautifully for objects and phenomena within our reach. You can measure the mass of a planet, the temperature of a star, the distance to a galaxy. Each measurement comes with uncertainty, but the uncertainty can be quantified, understood, and ideally reduced with better instruments. But when you try to measure the universe as a whole, when you ask questions about its total size, its overall shape, or whether it has an edge, you encounter limits that aren't just practical, but potentially fundamental. Consider the most basic question: how big is the universe? The observable universe, the part we can see, has a measurable size. It's determined by how far light has been able to travel since the Big Bang. That distance is about 46 billion light years in every direction, creating a sphere about 93 billion light years across. But that's just what we can observe. The actual universe, the whole of space, might be much larger. It might even be infinite. How do you measure something that might be infinite? How do you test the hypothesis that the universe goes on forever? You can't observe it all. You can't travel to the edge, if there is one, and confirm it's there. The limitation isn't technological. It's built into the structure of space-time itself. Information can't travel faster than light, and space is expanding. So there are regions of the universe whose light will never reach us no matter how long we wait. The observable universe is all we can ever access, and it might be only a tiny fraction of the whole. This creates a peculiar situation where we have questions that can't be answered through observation. Is the universe infinite or finite? Does it have an edge, or does it curve back on itself? These questions seem scientific. They're about the physical structure of reality, but they might be permanently beyond the reach of empirical investigation. We can construct models, make assumptions, see which ones fit the data we have. But we might never be able to definitively prove which model is correct. The contradiction deepens when you consider the nature of scientific explanation itself. Science works by breaking complex phenomena into simpler components, by finding patterns and laws that describe how things behave. But the universe as a whole can't be broken down into components. It's the ultimate context, the framework within which everything else exists. There's no outside perspective from which to view it, no external reference frame for comparison. We're inside the system we're trying to understand, using tools and minds that are themselves products of that system. This self-referential quality makes cosmology unique among sciences. When a biologist studies a cell, she stands outside the cell, observing it through a microscope. When a physicist studies a particle, he sets up an experiment that isolates the particle from other influences. But when a cosmologist studies the universe, there's no standing outside. Every observation is made from within, every measurement coloured by our location in space and time. We can only see the universe from one perspective, our own, and that perspective is necessarily limited. The mystery enters where measurement ends. Beyond the cosmic horizon, beyond the farthest light we can detect, lies territory that is real but forever unknowable through direct observation. We can speculate about it. We can extrapolate from what we see nearby. We can assume that the laws of physics are the same everywhere and use those laws to predict what might exist beyond our view. But we can't test those predictions. The mystery remains intact, untouchable by experiment. Some scientists are comfortable with this. They argue that science isn't about knowing everything. It's about knowing what can be known and being honest about the limits of knowledge. Others find it frustrating, a boundary that shouldn't exist, a question that should have an answer but doesn't. The tension between these views has shaped cosmology for decades, influencing which questions get pursued and which theories get taken seriously. The contradiction also appears in the language we use to describe the universe. Words like edge, boundary, and end carry everyday meanings that don't quite translate to cosmic scales. When we say the universe might have no edge, we don't mean it's infinite in the way that numbers are infinite, stretching endlessly in one direction. We mean something more subtle. That space might curve back on itself so that travelling far enough in any direction brings you back to where you started, like walking around the surface of a sphere. There's no edge to a sphere's surface, but the surface is finite. But try to visualize that in 3 dimensions instead of 2, and the mind struggles. We can write the mathematics, we can solve the equations, we can make predictions about what such a universe would look like. But we can't picture it, can't hold it in imagination the way we can picture a sphere. The contradiction is between mathematical understanding, which is precise and clear, and intuitive understanding, which requires images and analogies that sometimes don't exist. Mystery also lies in the questions that science opens up rather than closes. The Big Bang explains how the universe evolved from a hot, dense state, but it doesn't explain why there was a hot, dense state to begin with. It pushes the question of ultimate origin back to a moment we can't observe, a singularity where our equations break down and our concepts lose meaning. We know the universe began, but we don't know why, or how, or what, if anything, came before. Perhaps where they merge. The question of why there is something rather than nothing isn't a scientific question in the traditional sense. You can't design an experiment to answer it, but it's intimately connected to scientific cosmology, arising naturally from the evidence that the universe had a beginning. Science can describe what happened, but it can't, at least not yet, explain why it happened. The mystery remains, sitting at the foundation of all our knowledge. The contradiction between science and mystery is also about timescales. Science works on human timescales. We make observations, form hypotheses, test predictions, revise theories. The process takes years or decades, or at most centuries. But the universe operates on timescales of billions of years. The light we see from distant galaxies began its journey long before human civilization existed. The structures we observe today formed over periods longer than all of recorded history. How do you test theories about events that took billions of years to unfold? You can't speed up cosmic evolution to see what happens. You can't rerun the Big Bang with slightly different conditions to see how the outcome changes. All you can do is observe the universe as it is now. Try to reconstruct its past from present evidence, and use that reconstruction to predict what future observations will show. It's historical science, detective work on the grandest possible scale, and it requires leaps of inference that go far beyond laboratory experiments. The mystery also touches on consciousness itself. We are the universe, trying to understand itself, matter organized in such a way that it can contemplate its own existence. That self-referential loop is strange and perhaps unique. As far as we know, we're the only part of the universe capable of asking where the universe ends. That ability to question, to wonder, to seek understanding, seems to be a rare and precious phenomenon, and it exists in tension with the vastness and indifference of the cosmos. The universe doesn't care whether we understand it. It follows its own laws, evolves according to its own logic, completely independent of our observations or theories. And yet, somehow, we do understand it, at least partially. The mathematics we invent to describe subatomic particles also describes the behavior of galaxies. The equations work at scales from the infinitesimal to the cosmic. This unreasonable effectiveness of mathematics, as one physicist called it, is itself a kind of mystery. Why should the universe be comprehensible? Why should human reason be adequate to grasp cosmic truth? The contradiction between science and mystery isn't something to be resolved. It's something to be lived with, navigated, even embraced. Science gives us tools, methods, evidence. Mystery gives us humility, wonder, the recognition that our knowledge is always partial and provisional. Together, they create a dynamic tension that drives exploration forward. We measure what we can, knowing that beyond every measurement lies something we can't measure. We build theories, knowing that every theory has limits. We ask questions, knowing that some questions might never be answered. And perhaps that's appropriate for creatures like us, finite beings contemplating infinity, temporary forms pondering eternity. The contradiction between science and mystery mirrors the contradiction of our existence. We know we're small, brief, limited, and yet we reach for understanding that transcends those limits. We can't see the whole universe, but we can imagine it. We can't live forever, but we can think about time spans that dwarf our lives. The tension between what we are and what we can conceive is the same tension between science and mystery. And it's what makes cosmology not just a technical discipline, but a deeply human endeavor. When scientists first grappled with the idea that the universe might have an edge, or might not have an edge, or might have something stranger than either option, they split into camps. Not hostile camps, not opposing armies, but different schools of thought shaped by different intuitions about how reality should work. The divide wasn't just about data. It was about what kind of universe made sense, what kind of cosmos we could live in comfortably, what our minds were willing to accept. One group argued that the universe must be finite. It had a beginning, they reasoned, so it must have bounds. The Big Bang started everything from a dense, hot state, and that state must have had a definite size, however small. As the universe expanded, it grew larger, but it remained finite. A bounded region of space, surrounded by what? Nothing. Not even nothing. The absence of space itself. This view appealed to those who liked their cosmology neat, with clear boundaries and definite numbers. Another group insisted the universe must be infinite. If it was infinite now, they argued, then it was infinite at the Big Bang as well. Infinity doesn't shrink to finite just because distances contract. The expansion meant that any given distance grew larger, but an infinite space remained infinite throughout. This view avoided the uncomfortable question of what lay beyond a finite universe's edge, but it raised equally uncomfortable questions about how something infinite could begin, how you could have infinite matter and energy emerging from a single moment. A third group proposed something more subtle. Maybe the universe was finite but unbounded, like the surface of a sphere. There's no edge to a sphere's surface. You can walk around it forever without finding a boundary, and yet it has a definite, measurable area. Applied to three-dimensional space, this meant the universe could curve back on itself, travel far enough in one direction, and you'd eventually return to your starting point, having circled the entire cosmos. It was finite in volume, but had no edge, no boundary, no place where space simply stopped. Weren't just abstract mathematical possibilities. Each theory made different predictions about what we should observe. A finite, bounded universe would have an edge we could potentially detect. A place where the density of galaxies dropped off, where space became noticeably different. An infinite universe would look more or less the same in all directions, uniformly filled with structure no matter how far you looked. A curved, closed universe would show subtle patterns in the cosmic microwave background, signatures of the curvature in the way light travelled across space. The divide among theorists reflected deeper philosophical differences. Some valued simplicity, preferring models with the fewest assumptions and the cleanest mathematics. Others valued completeness, wanting theories that answered every question, even if that meant adding complexity. Some were empiricists, trusting only what could be directly observed and measured. Others were rationalists, willing to follow to mathematical logic, even when it led to conclusions that couldn't be tested. There was also disagreement about what the expanding universe meant for the concept of an edge. If space itself was expanding, carrying galaxies apart, did that mean the universe was growing into something? Or was it simply that the distances between existing points were increasing? If it was growing into something, then there must be a boundary where expansion stopped, an edge beyond which the expansion hadn't yet reached. But if distances were just increasing, then there need be no edge at all. The expansion could be happening everywhere equally, with no center and no boundary. This question divided even those who accepted the expansion. Some visualized it as a bubble growing larger, with the Big Bang at its center and the expanding universe filling more and more of some pre-existing space. Others rejected that image entirely, insisting that space itself was created by the expansion, that there was no pre-existing stage on which the cosmic drama unfolded. The universe didn't expand into anything. It simply expanded, creating more space as it went. The mathematics of general relativity allowed for both possibilities. Einstein's equations were flexible enough to describe many different cosmic geometries: flat, curved, open, closed. Which one actually described our universe was a matter for observation to decide, not theory alone, but the observations weren't conclusive. Measurements of the universe's curvature showed it to be very close to flat, but close to flat could mean exactly flat and infinite, or it could mean slightly curved and very large but finite. The data couldn't quite distinguish between these options. As technology improved and telescopes became more sensitive, the divide among theories narrowed but didn't close. The cosmic microwave background, that faint afterglow of the Big Bang, provided the most detailed information yet about the universe's geometry. Its pattern of tiny temperature variations encoded information about the curvature of space. Teams of scientists analyzed those patterns with extraordinary precision, looking for the telltale signs of curvature. The results showed the universe was flat to within a small margin of error. Not curved like a sphere, not curved like a saddle, but flat like a Euclidean plane. This supported the idea that the universe might be infinite, because flat geometry typically extends forever. But it didn't prove infinity. The universe could still be flat and finite if it had an unusual topology, if it wrapped around itself in ways that preserved flatness on local scales while creating a finite total volume. This led to a new divide between those who thought the simplest interpretation, infinite, flat space, was most likely correct, and those who explored more exotic topologies, donut-shaped universes, or more complex structures, where space connected to itself in intricate ways. These ideas were mathematically valid and consistent with observations, but they seemed unnecessarily complicated to some and fascinatingly possible to others. The divide also reflected different attitudes toward the unknowable. Some scientists were comfortable saying that if the universe extended beyond the observable horizon, we'd never know how far it went or whether it had an edge. They saw this as a natural limit to scientific knowledge, a boundary we should accept rather than fight. Others chafed at this limitation, seeking ways to extract information about the unobservable universe from subtle effects on what we could see. Perhaps the distribution of galaxies within our horizon carried signatures of structure beyond it. Perhaps quantum fluctuations in the early universe preserved hints about the total size of the cosmos. The theories divided further when dark energy entered the picture. The discovery that the universe's expansion was accelerating, driven by some unknown energy filling empty space, changed the entire discussion about edges and boundaries. Dark energy seemed to be a property of space itself, present everywhere equally. As the universe expanded and created more space, it also created more dark energy, which drove even faster expansion. This meant that the cosmic horizon, the boundary of what we could ever observe, was now fixed. Galaxies beyond a certain distance would recede so fast that their light would never reach us, even given infinite time. This created a practical edge, even if there wasn't a physical one. The observable universe had a definite size that wouldn't grow much larger in the future. In fact, it would eventually shrink as distant galaxies accelerated away, their light stretched beyond detectability. Observers in the far future would see a smaller, darker universe than we see now, with fewer galaxies and less evidence of cosmic expansion. The edge wasn't spatial, it was observational, informational, a boundary between what could be known and what was forever hidden. Some theories proposed that this acceleration was temporary, that dark energy might change over time, eventually weakening and allowing gravity to regain control. Others suggested dark energy was a constant, the cosmological constant Einstein had once introduced and then abandoned, now returning as a fundamental property of empty space. Each version led to different predictions about the universe's ultimate fate and whether we'd ever be able to see beyond our current horizon. The divide among theories ultimately came down to a simple question: which is more disturbing, a universe with an edge or a universe without one? An edge meant there was something beyond, even if that something was just the absence of space, and it raised questions about what defined the boundary and why space stopped there. No edge meant the universe went on forever, potentially infinite, containing infinite galaxies and infinite possibilities. a concept that strained credulity even as it satisfied certain mathematical principles. Different minds found different answers to that question. Some embraced infinity as the natural state of things, the simplest assumption. Others found it absurd and preferred a large but finite cosmos. Still others remained agnostic, willing to wait for more evidence before committing to either view. The theories divided not because scientists disagreed about the data, which was largely accepted by all, but because they interpreted that data through different philosophical frameworks, different intuitions about what kind of universe made sense, and perhaps that's appropriate. The question of where the universe ends, if anywhere, touches on matters of existence and meaning that go beyond mere measurement. It's a question that engages not just our scientific understanding, but our sense of wonder, our need for comprehension, our relationship with the infinite. The theories divide because we divide, because different people find different ways of making peace with the vastness that surrounds us. And in that division, in that multiplicity of perspectives, we see the full range of human thought grappling with the cosmos. The pursuit of where the universe ends became one of astronomy's defining quests, a question that would occupy generations of scientists and drive the construction of increasingly powerful telescopes. It wasn't a pursuit that could be satisfied with a single observation or a simple measurement. It required patience, technology, and a willingness to chase answers that might forever remain just out of reach. In the decades following Hubble's discovery of cosmic expansion, astronomers set out to map the universe more completely. They wanted to know not just that galaxies were moving apart, but how fast, how uniformly, and whether the expansion was constant or changing over time. These questions required measuring distances to galaxies far beyond the reach of Cepheid variables, beyond even the brightest stars. They needed new tools, new techniques, new ways of extracting information from faint light that had travelled across billions of years. The investigation took many forms. Some astronomers focused on cataloguing galaxies, creating maps that showed their distribution across the sky. The first surveys revealed that galaxies weren't scattered randomly. They formed clusters, groups of hundreds or thousands of galaxies bound together by gravity. And those clusters themselves seemed to be arranged in larger structures, superclusters, and filaments that stretched across hundreds of millions of light years. This cosmic web, as it came to be called, suggested that the universe had structure on the largest scales. It wasn't uniform in detail, even if it was uniform on average. Matter had clumped together under gravity's influence, forming dense regions separated by vast voids where few galaxies existed. Understanding this structure became crucial to understanding the universe's overall geometry. If you could trace the pattern of matter across space, you could infer the curvature, the density, and potentially whether space extended infinitely or curved back on itself. Other astronomers pursued the expansion rate directly. They developed new distance indicators, ways of measuring how far away galaxies were. Supernovae, the explosive deaths of certain types of stars, proved particularly useful. Type Ia supernovae, which occur when white dwarf stars accumulate too much mass and detonate, shine with a consistent brightness. Like Cepheid variables, they could be used as standard candles. Measure how bright they appear, compare that to their known true brightness, and you can calculate their distance. These supernova observations required patience. Type Ia supernovae are rare, perhaps one per century in any given galaxy. To find enough of them to make meaningful measurements, astronomers had to monitor thousands of galaxies over years, waiting for stars to explode. The supernova would brighten quickly and fade over weeks, so measurements had to be made promptly, tracking the light curve precisely to determine the peak brightness. The pursuit also involved theoretical work. using mathematics and physics to predict what different types of universes would look like. If the universe was closed and finite, light traveling across it would show subtle effects of the curvature. If it was flat and infinite, the geometry would be Euclidean, following the rules we learn in school. If it was open and negatively curved, like a saddle shape extended to 3 dimensions, the angles of triangles would add up to less than 180 degrees. These predictions gave observers specific things to look for. They could measure the cosmic microwave background, that faint afterglow of the Big Bang, and check whether its patterns match the predictions for flat, closed, or open geometry. They could count galaxies at different distances and see whether the distribution matched what each model predicted. They could measure the relationship between distance and velocity, checking whether Hubble's linear law held at extreme ranges or whether deviations appeared that would reveal the universe's ultimate fate. The investigation required new instruments. Larger telescopes with bigger mirrors could collect more light, revealing fainter and more distant objects. Better detectors replaced photographic plates, capturing light with greater efficiency and sensitivity. Computers analyzed the data, finding patterns human eyes would miss. Each advance pushed the boundary of observation a little farther outward, adding more galaxies to the cosmic map, extending the measured expansion to greater distances. Space-based telescopes joined the effort. The Hubble Space Telescope, launched in 1990, orbited above Earth's atmosphere, which blurs and distorts light from distant objects. From space, Hubble could see with unprecedented clarity, resolving details in galaxies billions of light years away. It captured deep-field images, photographs of tiny patches of apparently empty sky that turned out to contain thousands of galaxies, each one a vast structure of billions of stars, all crowded into a region smaller than a grain of sand held at arm's length. These deep fields revolutionized the investigation. They showed that wherever you looked, no matter how empty a patch of sky appeared, it was filled with galaxies extending to enormous distances. The universe wasn't thinning out. It wasn't showing signs of an edge. It looked more or less the same in all directions, as far as we could see. This uniformity supported the idea that the universe was either infinite or, if finite, much larger than the observable portion we could study. The pursuit also involved understanding light itself more deeply. When light travels across expanding space, it gets stretched, its wavelength increasing, its color shifting toward red. Of stretching depends on how much the universe has expanded during the light's journey. Measure the redshift precisely, and you can determine not just the distance but also when the light began its journey. This turns every galaxy into a time marker, showing us the universe at different ages. Spectroscopy became crucial. By splitting light into its component wavelengths and analyzing the resulting spectrum, astronomers could identify specific elements in distant galaxies: hydrogen, helium, oxygen, iron. Each element absorbed or emitted light at characteristic wavelengths. When those wavelengths were all shifted by the same amount, it confirmed that the shift was due to cosmic expansion, not some other effect. And by measuring the shift precisely, observers could place each galaxy at its correct distance and time. The investigation faced constant challenges. Measuring distances to remote galaxies wasn't straightforward. Each technique had uncertainties, and those uncertainties compounded when multiple steps were required. The distance ladder, as it's called, starts with nearby objects measured through parallax, moves to Cepheid variables in more distant galaxies, then to supernovae in galaxies beyond the reach of Cepheids. Each rung depends on the previous one, and errors accumulate. Observers had to account for dust, which dimmed light, and made objects appear farther than they were. They had to correct for the motion of the Milky Way itself, which affected apparent velocities. They had to deal with the fact that galaxies at different distances were seen at different evolutionary stages, when their properties might have been different from what we observe nearby today. Each correction required assumptions, and those assumptions had to be tested and refined through careful comparison of different methods. The pursuit also revealed unexpected phenomena. Gravitational lensing, predicted by general relativity, bent light from distant galaxies as it passed near. Massive clusters. Sometimes this created multiple images of the same galaxy, distorted arcs that traced the path of light around the intervening mass. These lensing events became tools in themselves, allowing astronomers to measure the mass of the lensing clusters and map the distribution of dark matter, the invisible substance that provided most of the gravity. As the investigation progressed, the cosmic horizon became clearer. The observable universe had a definite size, limited by the finite age of the cosmos and the finite speed of light. But that boundary wasn't fixed in space. It was growing. Every second, light from regions previously beyond our view entered the observable universe for the first time. The horizon expanded constantly, though slowly, revealing more of the cosmos with each passing year. Yet even as the horizon grew, astronomers realized that some parts of the universe were slipping beyond reach. The accelerating expansion meant that galaxies beyond a certain distance were receding so fast that their light, though traveling toward us, never gained ground. They remained forever beyond our horizon, their information unable to reach us no matter how long we waited. The investigation had found not an edge to space, but an edge to knowledge, a boundary defined not by where space ended, but by which parts of space could communicate with us. The pursuit became more than scientific. It touched something deeper, a fundamental human drive to know where we stand, to understand our place in the whole. Every measurement, every calculation, every image captured by a telescope was an attempt to answer that ancient question that people have asked since they first looked up at the night sky. How far does it go? Where does it end? And what does it mean that we exist within it? The investigation continues today. New telescopes push farther into space and time. The James Webb Space Telescope, launched in 2021, observes the universe in infrared, light, seeing through dust, and detecting galaxies formed just a few 100 million years after the Big Bang. Ground-based observatories with mirrors 30 meters across are under construction, promising even deeper views. Each advance adds detail to the cosmic map, refines our measurements of the expansion rate, and brings us closer to understanding the universe's true geometry. But with each answer comes new questions. The pursuit of where the universe ends has become a pursuit of understanding how it works, why it's structured the way it is, what forces shaped its evolution, and what fate awaits it. The edge, if there is one, remains elusive, but the pursuit itself has transformed our understanding of existence, revealing a cosmos far stranger, far larger, and far more beautiful than anyone imagined when the investigation began. And perhaps that's the real success of the pursuit. Not finding a final answer, but learning to ask better questions. Not reaching the edge, but understanding that the edge might not exist in any simple sense. Not solving the mystery, but learning to live with it, to explore it, to follow its implications wherever they lead. The investigation continues, patient and persistent, driven by curiosity and wonder, seeking the boundaries of the knowable. The universe speaks to us in data, not in words or images, not in direct revelation, but in subtle patterns hidden in light. Every photon that reaches our telescopes carries information encoded in its wavelength, its energy, its direction of travel. Collecting that information, interpreting it, and assembling it into coherent understanding is the work of cosmology. And the data, accumulated over decades of patient observation, has begun to sketch the outline of an answer to our question. The first clue comes from the cosmic microwave background, that faint afterglow of the Big Bang filling the entire sky. When satellites map this background with extraordinary precision, measuring temperature variations across the sky to millionths of a degree, they found patterns. The background wasn't perfectly uniform. It had tiny ripples, regions slightly warmer or cooler than average, variations that reflected the density of matter in the early universe. These ripples weren't random. They had a characteristic scale, a size that appeared again and again across the sky. That scale was determined by how far sound waves could travel through the hot plasma of the early universe before it cooled and became transparent. Measure that scale, and you can infer the curvature of space, because curvature affects how large distant objects appear. It's like looking at a pattern on a sphere versus a flat surface versus a saddle. The geometry changes the apparent size. The data showed that the universe was flat, or so close to flat that the curvature was unmeasurable. The angles added up correctly. The patterns had the right size. Space, on the larger scales we could observe, followed Euclidean geometry. This was a crucial clue, because flat geometry typically extends infinitely. You can draw parallel lines that never meet, and you can keep going in any direction forever without the space curving back on itself. But flat doesn't guarantee infinite. It's possible for a space to be flat and still have a finite volume if it wraps around itself in unusual ways. Imagine a video game where walking off the right edge of the screen makes you appear on the left edge. The local geometry is flat, you move in straight lines, but the total space is finite. The universe could work similarly, connecting distant regions in ways that create a finite but unbounded volume. Astronomers looked for evidence of such topology by searching for repeated patterns in the cosmic microwave background. If the universe wrapped around itself, we might see the same structures appearing in opposite directions. Cosmic déjà vu, where light had travelled around the universe and arrived from multiple angles. The searches found nothing. No clear repetitions, no obvious signs that space looped back on itself. The simplest interpretation was that the universe was flat and large enough that any looping happened at scales far beyond what we could observe. Another clue came from counting galaxies. If you divide the sky into regions and count how many galaxies appear in each one, you can test whether the universe is uniform. A finite universe with an edge might show variations in galaxy density depending on which direction you looked. An infinite universe, or a finite one much larger than the observable portion, should show uniform density on average. The same number of galaxies per volume regardless of direction. The data confirmed uniformity. Every deep survey, every catalogue of distant galaxies showed the same thing. The universe looked the same in all directions. There was no preferred direction, no axis along which things were different. This isotropy, combined with the assumption that we don't occupy a special location, implied that the universe was homogeneous, essentially the same everywhere, and a homogeneous universe either extends infinitely or curves back on itself with no center or edge. Distance measurements provided more clues. By observing Type Ia supernovae at various distances, astronomers could measure how the expansion rate had changed over time. Light from nearby supernovae showed the universe as it was relatively recently. Light from distant ones showed the universe billions of years ago. Comparing the two revealed how fast the universe was expanding at different epochs. The data showed something unexpected. The expansion wasn't slowing down, as most theorists had assumed. It was speeding up. Distant supernovae were farther away than they should be if the expansion had remained constant or decelerated. This implied that some force was driving the acceleration, pushing galaxies apart faster and faster. That force, dubbed dark energy, has become one of the deepest mysteries in cosmology. Dark energy changed the data's implications for where the universe ends. If the expansion is accelerating, then there's a cosmic event horizon, a boundary beyond which galaxies are receding so fast that their light will never reach us. This horizon sits at a fixed distance in co-moving coordinates, meaning it doesn't grow with time the way the observable universe's edge does. In fact, galaxies that are currently visible will eventually accelerate beyond this horizon and disappear from view as their light redshifts into invisibility. The data also revealed the universe's composition by combining measurements of the cosmic microwave background, galaxy distributions, and supernova distances. Cosmologists could determine what the universe is made of. The results were surprising. Ordinary matter, the atoms that make up stars, planets, and people, accounts for less than 5% of the total. About 27% is dark matter, invisible, substance that interacts through gravity, but not light. And the remaining 68% is dark energy, the mysterious force driving cosmic acceleration. This composition affects where the universe ends because it determines how space curves. Too much matter, and gravity would curve space into a closed, finite shape. Too little, and space would curve negatively into an open, infinite shape. The data showed that the total density was almost exactly at the critical value separating these possibilities, which corresponds to flat geometry. The universe sits balanced on the knife edge between closure and infinite extent. Fragments of data from gravitational lensing added another layer of understanding. When light from distant galaxies passes near massive clusters, the gravity of those clusters bends the light, distorting the images. By studying these distortions, astronomers can map the distribution of mass, including the dark matter that provides most of the gravitational pull. The bin resulting maps show a cosmic web of filaments and clusters with vast voids between them. This web extends as far as we can see, showing no signs of thinning out or changing character near the edge of the observable universe. The structure we observe nearby continues to similar distances in all directions, suggesting that the universe beyond our horizon likely looks much the same. It shows continuity, a cosmos that extends smoothly beyond what we can observe. Quasar spectra provided clues about the universe's history. Quasars are incredibly bright galactic cores powered by supermassive black holes. They're so bright that we can see them across most of the observable universe, making them useful probes of cosmic evolution. By analyzing the light from quasars at different distances, astronomers can track how the universe's contents have changed over time, how galaxies have evolved, and how the expansion rate has varied. The data showed consistency. The laws of physics appear to be the same at all distances and times. The same elements, the same fundamental constants, the same forces at work. This uniformity supports the idea that the universe beyond our horizon is similar to what we see within it. There's no indication that conditions change dramatically at large distances, no hint of an edge where the rules become different. But the data also has limits. We can only see so far, only measure so precisely. The uncertainties in our measurements leave room for possibilities we can't rule out. The universe could be slightly curved in ways too subtle to detect. It could have exotic topology that manifests only at scales larger than the observable universe. It could be part of a larger multiverse, forever beyond our ability to observe directly. The clues and fragments, when assembled carefully, paint a picture of a universe that's flat, homogeneous, isotropic, and likely either infinite or vastly larger than the part we can see. The data doesn't show an edge. It shows a cosmos that continues uniformly in all directions to the limit of observation. But the limit of observation isn't the limit of existence. Beyond our cosmic horizon, the universe extends, following the same laws, containing more galaxies, more stars, more structure that we'll never witness. The data has transformed the question of where the universe ends from philosophy to physics. We can measure the observable universe's size, calculate how it's evolved, predict its future, but the data also shows us the limits of data itself. Some questions can't be answered through observation because the information simply can't reach us. The universe has built-in boundaries to knowledge, horizons beyond which we cannot see no matter how powerful our telescopes become. And yet, even within those limits, the data is rich with meaning. Every measurement constrains possibilities, rules out models, guides theory toward truth. The clues and fragments don't give us a final answer about where the universe ends, but they give us something equally valuable, a deepening understanding of what the universe is, how it works, and our place within its vastness. The data speaks, and we listen, assembling its whispers into knowledge. Beneath the question of where the universe ends lies a deeper mystery, one that's even more perplexing than the geometry of space or the extent of cosmic structure. It's the mystery of what the universe is mostly made of, and the unsettling truth that nearly everything that exists is invisible to us, detectable only through its effects on the small fraction of matter that we can see. The first hints came from studying how galaxies rotate. In the 1970s, astronomer Vera Rubin measured the speeds of stars orbiting in spiral galaxies like the Milky Way. According to Newton's laws and Einstein's relativity, stars farther from the galactic center should orbit more slowly, just as outer planets in our solar system take longer to complete their orbits than inner ones. The math was straightforward. The more distant from the mass concentration, the weaker the gravitational pull, the slower the orbit. But that's not what Rubin found. Stars at the edges of galaxies were moving just as fast as those closer to the center, sometimes even faster. Their orbital speeds remained roughly constant regardless of distance. This shouldn't have been possible unless there was far more mass in the galaxy than visible stars could account for. Something unseen was providing the gravity to hold these fast-moving stars in their orbits. Something that didn't shine, didn't emit radiation, didn't interact with light in any way we could detect. This invisible substance came to be called dark matter, and subsequent observations confirmed it wasn't just in one galaxy or one cluster. It was everywhere. Galaxies were embedded in vast halos of dark matter, invisible clouds that extended far beyond the visible stars. Clusters of galaxies were held together by dark matter's gravity. The cosmic web itself, that grand structure of filaments and voids, was scaffolded by dark matter. The luminous matter we see, the stars and gas and dust, had simply fallen into the gravitational wells created by this unseen substrate. Estimating how much dark matter exists required careful measurements. By studying how galaxies move within clusters, how light bends around massive structures through gravitational lensing, and how the cosmic microwave background's patterns reflect matter's influence, cosmologists determined that dark matter outweighs ordinary matter by about 5 to 1. For every kilogram of atoms, there are roughly 5 kilograms of something else. Something that doesn't absorb or emit light, doesn't interact through electromagnetic forces, and reveals itself only through gravity. The hidden truth is that we don't know what dark matter is. Decades of searching have yielded no definitive detection of dark matter, particles, experiments deep underground, shielded from cosmic rays and other interference, wait for dark matter particles to collide with ordinary atoms, hoping to catch the rare interaction that would reveal their nature. So far, silence. Particle accelerators look for signs of dark matter production in high-energy collisions. So far, nothing. The dark matter stubbornly refuses to announce itself through any means except its gravitational influence. Theories abound. Perhaps dark matter consists of WIMPs, weakly interacting massive particles, hypothetical entities that feel gravity and the weak nuclear force but nothing else. Perhaps it's axions, ultralight particles that would fill space like an invisible fog. Perhaps it's primordial black holes formed in the early universe before stars existed. Perhaps it's something more exotic, particles or phenomena we haven't imagined yet because they require physics beyond our current theories. The mystery deepens with dark energy, the even more enigmatic force driving the universe's accelerating expansion. If dark matter accounts for 27% of the universe's total energy content, dark energy makes up 68%. It's the dominant component, the thing that will ultimately determine the universe's fate, and we understand it even less than we understand dark matter. Dark energy doesn't clump like matter does. It's distributed uniformly throughout space, a kind of cosmic pressure that pushes outward rather than pulling inward through gravity. Its density remains constant as the universe expands, which means that as space grows, the total amount of dark energy increases. More space means more dark energy, which drives faster expansion, which creates even more space. It's a runaway process that will continue indefinitely, accelerating without bound. The simplest explanation for dark energy is that it's a property of space itself, what Einstein called the cosmological constant. Empty space, in this view, has inherent energy. The vacuum isn't truly empty but seething with quantum fluctuations, virtual particles that pop in and out of existence. Those fluctuations contribute to the energy density of space, and that energy manifests as dark energy, driving the cosmic acceleration. When physicists calculate what the vacuum energy should be based on quantum field theory, they get a number that's vastly larger than what we observe, off by a factor of 10 to the power of 120. It's the worst prediction in the history of physics, a discrepancy so enormous that it suggests we're fundamentally misunderstanding something about how quantum mechanics and gravity interact. Why is the observed dark energy density so much smaller than theory predicts? No one knows. Alternative theories propose that dark energy isn't constant but varies over time, a field that changes as the universe evolves. This would make it more like a fifth fundamental force, something dynamic, rather than a fixed property of space. But observations so far show that dark energy's density has remained remarkably constant across billions of years of cosmic history. If it's changing, it's doing so very slowly, within narrow bounds that current measurements can't distinguish from perfectly constant. The hidden truth that dark matter and dark energy reveal is that the universe we can see, the stars and galaxies and glowing nebulae, represents only a tiny fraction of what exists. Everything we've ever observed, every photon we've collected, every particle we've detected in accelerators, all of it together makes up less than 5% of the cosmic inventory. The rest is dark, hidden, operating through channels we can barely perceive. This has profound implications for where the universe ends. If we can only see 5% of what's out there, how can we claim to understand the whole? The dark matter and dark energy might be distributed uniformly beyond our horizon, continuing the same patterns we observe nearby. Or they might behave differently at scales we can't access. Perhaps dark energy strengthens at large distances, or perhaps dark matter has structures we haven't imagined because we can only see its effects through the small amount of ordinary matter it influences. The mystery also touches on the nature of space itself. If dark energy is a property of the vacuum, then empty space isn't empty. It has energy, tension, pressure. It's an active player in cosmic evolution, not a passive backdrop. The expansion of the universe isn't just galaxies moving through space. It's space itself responding to the dark energy that fills it, growing in response to that energy's pressure, creating more of itself with every passing moment. Some theories suggest that dark energy could change phase, transitioning from one state to another the way water freezes into ice. If that happened, it could catastrophically alter the structure of space, rewriting the laws of physics, destroying everything that currently exists. This scenario, called vacuum decay, remains speculative but mathematically possible. It's a reminder that the hidden components of the universe, the things we don't understand, could hold surprises that reshape reality itself. The deeper mystery isn't just that most of the universe is hidden, it's that we're somehow able to detect it at all, to infer its existence from the subtle effects it has on the visible matter. The fact that dark matter's gravity bends light means we can map its distribution even though we can't see the matter itself. The fact that dark energy affects the expansion rate means we can measure it through observations of distant supernovae. We're like detectives reconstructing a crime scene from scattered clues, never seeing the perpetrator but deducing their actions from the evidence left behind. This indirect detection is one of science's great triumphs, a testament to the power of inference and reason. We can know things exist without seeing them directly, can measure their properties without touching them, can understand their influence without fully comprehending their nature. The hidden truth emerges through patient observation, careful analysis, and the mathematical frameworks that let us connect visible effects to invisible causes. But it's also humbling. We live in a universe where 95% of the content is mysterious, where the dominant forces shaping cosmic evolution operate through channels we're only beginning to probe. The question of where the universe ends becomes even more complex when we realize we don't know what most of the universe is made of. How can we claim to understand its extent, its shape, its ultimate fate, when we're missing so much of the picture? The answer is that we work with what we have. We measure the visible, infer the invisible, build models that account for both, and test those models against observation. The hidden truth constrains possibilities without revealing itself fully. We know dark matter exists because of how galaxies move. We know dark energy exists because of how the expansion accelerates. We may not know what they are, but we know what they do, and that knowledge is enough to make progress. The deeper mystery won't be solved quickly. Understanding dark matter and dark energy will require breakthroughs in fundamental physics, new theories that go beyond the standard model of particle physics and general relativity. It might require concepts we haven't imagined yet, mathematics we haven't developed, observations we haven't figured out how to make. The hidden truth might remain hidden for generations, revealing itself only gradually through accumulated evidence and theoretical insights. And perhaps that's appropriate. The universe doesn't owe us easy answers. It exists according to its own principles, indifferent to our desire for understanding. The fact that we've detected dark matter and dark energy at all, that we've measured their properties and understood their effects, is remarkable. The fact that mysteries remain, that the deepest truths stay hidden, keeps the pursuit alive. There's always more to learn, always another layer of mystery beneath the current one, always a deeper truth waiting to be uncovered. There are moments in science when everything changes. when a new discovery forces us to reconsider everything we thought we knew. These turning points are rare, often resisted at first, eventually accepted reluctantly, and finally understood as inevitable. The discovery that the universe's expansion is accelerating was one of those moments. It arrived quietly, through careful measurements of distant supernovae, and it shattered the comfortable assumptions cosmologists had been working with for decades. The expectation had been straightforward. The universe was expanding, yes, but that expansion should be slowing down. Gravity pulls everything together, so even as galaxies move apart, their mutual gravitational attraction should act as a brake, gradually reducing the expansion rate. The question cosmologists asked wasn't whether the expansion was decelerating, but how much. Would gravity slow it enough to eventually halt and reverse it, leading to a big crunch? Or would the expansion continue forever, just at an ever-decreasing rate? Two teams of astronomers set out to answer this question in the 1990s. They used Type Ia supernovae as cosmic measuring sticks, observing these exploding stars in distant galaxies to determine how far away they were and how fast space was expanding when their light began its journey. By comparing nearby supernovae, showing the universe's recent state, with distant ones, showing the universe billions of years ago, they could measure how the expansion rate had changed over time. The work was painstaking. Each supernova had to be caught quickly after it exploded, then observed repeatedly as it brightened and faded, its light curve measured precisely to determine its peak brightness. The analysis required careful calibration, correcting for dust that might dim the light, accounting for the supernova's exact type and properties, ensuring that the measurements were reliable and consistent. When both teams independently analyzed their data in 1998, they found something no one expected. The distant supernovae were fainter than they should be, which meant they were farther away than predicted. If the expansion had been slowing down, those supernovae should have been closer. The only way to make sense of the data was to accept that the expansion hadn't slowed. It had sped up. The turning point wasn't just about correcting a prediction, it was about fundamentally rethinking the universe's contents and fate. If the expansion was accelerating, something had to be driving that acceleration, some force or energy that overpowered gravity's pull. The teams cautiously proposed that Einstein's cosmological constant, long abandoned as unnecessary, might actually be real. Empty space might have energy, a kind of vacuum pressure that pushed outward rather than pulling inward. The scientific community responded with skepticism. Extraordinary claims require extraordinary evidence, and accelerating expansion was certainly extraordinary. Alternative explanations were proposed. Perhaps the distant supernovae were intrinsically different from nearby ones, dimmer for reasons unrelated to distance. Perhaps dust in the early universe was absorbing light in unexpected ways. Perhaps the analysis had subtle errors that mimicked the appearance of acceleration, but as more data accumulated, as both teams refined their measurements and found the same result, as other lines of evidence began to support accelerating expansion, the skepticism gradually gave way to acceptance. The cosmic microwave background measurements confirmed that the universe's total energy density matched predictions only, if you included dark energy. Galaxy surveys showed that the distribution of structure across cosmic history fit models with acceleration. Independent techniques all pointed to the same conclusion. The paradigm shift was complete. The universe wasn't just expanding, it was accelerating, driven by dark energy that made up nearly 70% of everything that exists. This changed the entire cosmic narrative. Instead of a universe gradually slowing down, potentially reversing into collapse, we lived in a universe racing toward an increasingly rapid expansion, one where galaxies would eventually recede so fast that their light could never reach each other. The turning point affected how we think about where the universe ends. With acceleration, there's a cosmic event horizon, a boundary beyond which galaxies are receding faster than light can travel. Objects beyond this horizon are fundamentally unobservable, not because we lack good enough telescopes, but because the information from them can never reach us. Even light traveling at maximum speed can't overcome the expansion of space carrying those regions away. This horizon sits at a fixed distance in co-moving coordinates, about 16 billion light-years away in the current epoch. Galaxies beyond this distance are receding so fast that light they emit now will never reach us, though we can still see light they emitted in the past when they were closer. Over time, as the acceleration continues, this horizon remains roughly constant while galaxies continue to cross it, disappearing from view one by one as they accelerate beyond the boundary of observability. The paradigm shift also changed predictions about the universe's ultimate fate. Without acceleration, cosmologists debated between eternal expansion and eventual collapse. With acceleration, the answer became clear. The universe will expand forever, and not just expand, but accelerate indefinitely. The expansion rate will approach a constant value determined by dark energy's density, and space will grow exponentially, doubling in size at regular intervals. In this future, distant galaxies fade from view as their light redshifts beyond detectability. The cosmic microwave background grows fainter and cooler, eventually becoming undetectable. Stars burn out and aren't replaced because the gas to form new ones gets dispersed by expansion. Eventually, only gravitationally bound structures remain visible, the local group of galaxies held together by gravity strong enough to resist the expansion. Everything else disappears beyond the horizon, leaving future observers in a small, dark, lonely universe. The turning point revealed something profound about timing. We live in an era when the universe still reveals its history. The cosmic microwave background is still detectable. Distant galaxies are still visible. The evidence of the Big Bang and cosmic evolution is still accessible. But this era won't last forever. Trillions of years from now, when the acceleration has carried distant structures beyond all horizons, when the background radiation has cooled into invisibility, future observers won't have the evidence we have. They'll live in a universe that appears static, eternal, and small, with no obvious signs of its dynamic past. This realization adds poignancy to our own observations. We happen to exist at a moment when the universe is old enough to have formed complex structures like stars, planets, and life, but young enough that we can still see deep into cosmic history. It's a narrow window in time, and we're fortunate to be looking through it while it remains open. The paradigm shift also raised new mysteries. What is dark energy? Why does it have the density it does? Why did it only recently begin to dominate the universe's evolution, taking over from matter's gravitational influence? For most of cosmic history, matter dominated, shaping the formation of galaxies and structure. Only in recent billions of years did dark energy become the primary force, driving acceleration. Why now? Why this cosmic epoch? These questions remain unanswered. Dark energy might be Einstein's cosmological constant, a fixed property of space that never changes. Or it might be something dynamic, a field that varies over time, though so slowly we haven't detected the variation yet. Different theories make slightly different predictions about the universe's future, but current observations can't distinguish between them. We know dark energy exists and drives acceleration, but we don't know what it fundamentally is. The turning point of discovering accelerating expansion transformed cosmology from a science focused on the universe's past to one equally concerned with its future. The Big Bang explained our origin. Dark energy determines our destiny. Both are equally mysterious in their own ways, and both define the boundaries of what we can know about cosmic extent and evolution. And perhaps the deepest impact of the paradigm shift is philosophical. It showed us that the universe is stranger than we imagined, that reality doesn't conform to our expectations or preferences. We wanted a universe that made intuitive sense, where gravity slowed expansion and everything stayed within reach. Instead, we got a universe that accelerates away from itself, where most of space will eventually become permanently inaccessible, where observation has fundamental limits not because of technology but because of cosmic structure itself. The turning point wasn't just about discovery, it was about accepting that the cosmos operates according to its own logic, not ours. And in that acceptance, in that willingness to follow evidence wherever it leads, even when it contradicts expectations, we find both humility and wonder. The universe surprises us because it's larger and stranger than our intuitions allow. And every surprise, every paradigm shift, reveals not just new facts but new possibilities, new ways of thinking about existence itself. When the discovery of cosmic acceleration became widely accepted in the early 2000s, the immediate ripple through the scientific community was profound. It wasn't just that one measurement had changed. It was that the entire framework for understanding the universe's fate needed revision. Textbooks had to be rewritten. Models had to be rebuilt. Cosmologists had to reconsider every assumption they'd been working with about where the universe was heading and what observations we could expect in the future. The most immediate consequence was the recognition that the observable universe had a finite future extent. This wasn't obvious at first. After all, we can currently see galaxies over 13 billion light-years away, and that observable region has been growing as light from more distant sources reaches us. But with accelerating expansion, that growth will eventually stop. There's a maximum distance we can ever observe, set by the cosmic event horizon, beyond which space expands too fast for light to ever reach us. This means that future astronomers, assuming any exist trillions of years hence, will have a smaller universe to study than we do now. Galaxies we can currently see will have crossed the horizon, their light stretched beyond detectability. The cosmic microwave background will have cooled and redshifted until it becomes indistinguishable from the faint glow of quantum fluctuations in space. The evidence for the Big Bang will have faded. Future observers will be left with a dark, quiet universe containing only their local gravitationally bound structures. The consequence for our understanding of where the universe ends is that the boundary keeps shifting. The edge isn't fixed in space but moves with time, and in the case of acceleration, it moves inward. More and more of the universe becomes unobservable as galaxies accelerate beyond our reach. The cosmic horizon contracts around us, not because we're losing ability to see, but because space itself is carrying information sources away faster than their signals can travel. Research priorities shifted immediately. If dark energy was real and dominant, understanding it became the most important problem in cosmology. New missions were proposed, new telescopes designed specifically to measure dark energy's properties with greater precision. The goal was to determine whether dark energy was truly constant, as Einstein's cosmological constant would be, or whether it varied with time. If it varied, that would point toward new physics, fields, or phenomena not included in current theories. The immediate ripple also affected how cosmologists interpreted existing data. Observations of the cosmic microwave background, of galaxy distributions, of gravitational lensing, all had to be reanalyzed in light of dark energy's presence. The models used to extract information from these observations had assumed particular expansion histories. With acceleration, those histories changed, and so did the interpretation of what the data revealed about the universe's composition, geometry, and evolution. One significant consequence was the refinement of the universe's age. With acceleration, the universe expanded faster in recent epochs than previously thought, which meant it took less time to reach its current size. The calculated age shifted slightly, settling at about 13.8 billion years. This age became more precisely determined as measurements of the cosmic microwave background and distant supernovae both constrained the expansion history consistently. The discovery also affected theories about the universe's beginning. If space has inherent energy that drives expansion, did that play a role in the inflationary epoch? The brief period of exponential expansion thought to have occurred in the first fraction of a second after the Big Bang. Inflation and dark energy might be related phenomena, both involving the energy of space itself, though, operating at vastly different energy scales. Understanding one might provide clues about the other. The immediate ripple extended to philosophy of science as well. The discovery demonstrated that the universe could surprise us, that our intuitions about how reality should work weren't reliable guides. The acceleration wasn't predicted. It wasn't expected. It contradicted what most cosmologists had assumed based on the obvious influence of gravity. The fact that observation revealed something completely unexpected reminded scientists to remain humble, to trust evidence over assumptions, to stay open to possibilities that seemed unlikely or counterintuitive. Public communication of cosmology changed too. Before the discovery, popular accounts of the universe's fate focused on the debate between eternal expansion and eventual collapse. After, the story became one of accelerating expansion toward a cold, dark, lonely future. This narrative was less dramatic than a big crunch, but perhaps more poignant. The universe wasn't heading toward catastrophic compression, but gradual isolation, a slow fading as structures drifted apart beyond all connection. Research funding reflected the shifted priorities. Experiments to detect dark matter and measure dark energy received increased support. Projects like the Dark Energy Survey, which mapped hundreds of millions of galaxies to trace how structure evolved over time, were launched. Space missions like the Planck satellite refined measurements of the cosmic microwave background to constrain dark energy's properties. The ripple of the discovery spread through the entire infrastructure of observational cosmology. Theoretical physics felt the consequence as well. If dark energy was real, then the vacuum of space had properties not fully accounted for in the standard model of particle physics or in general relativity. This suggested that combining quantum mechanics and gravity, the long-sought theory of quantum gravity, needed to explain not just extreme conditions like black holes or the Big Bang, but also the subtle energy of empty space that fills the entire universe. The cosmological constant problem, the discrepancy between predicted and observed vacuum energy, became more urgent. If space truly had intrinsic energy, why was that energy so much smaller than quantum field theory predicted? Some physicists proposed anthropic arguments, suggesting that in a multiverse with varying physical constants, only universes with small cosmological constants could form structures and support life, and therefore only such universes would have observers to ask the question. Others found this explanation unsatisfying and continued searching for dynamical mechanisms that could explain the observed value. The immediate ripple also touched on the nature of time. If the expansion will continue forever, accelerating indefinitely, then the universe has infinite future ahead of it. But that future will be increasingly empty, dark, and cold as stars burn out, black holes evaporate, and even protons potentially decay over timescales of 10 to the power of 100 years or more. The heat death of the universe, Once just one possible fate became the expected one, a gradual slide toward maximum entropy and minimum useful energy. This consequence affected how we think about the universe's story. It had a beginning at the Big Bang. It evolved through distinct eras, from radiation domination to matter domination to dark energy domination. And it has an ending of sorts, not a sudden termination but an asymptotic approach to emptiness, a universe that continues forever but becomes progressively less interesting, less dynamic, less capable of supporting complexity or life. The immediate ripple of discovering cosmic acceleration also unified several lines of research that had seemed separate. The study of distant supernovae, the analysis of the cosmic microwave background, the mapping of large-scale structure, all converged on the same picture. Dark energy was real, acceleration was happening, and the universe's composition and fate were now understood with unprecedented clarity. This convergence was itself a triumph, showing that different observational techniques all pointed to the same underlying truth. For individual researchers, the consequence was both exciting and unsettling. Exciting because cosmology had entered a new era with profound questions to answer. Unsettling because those questions might not have easy answers, might require physics beyond current theories, might even involve aspects of reality permanently beyond observation. The edge of knowledge had moved, revealing not just new territory, but new kinds of unknowability. Every new dark energy experiment, every improved measurement of the expansion rate, every theoretical proposal about the nature of vacuum energy, all stem from that initial discovery in the late 1990s. The consequence of finding cosmic acceleration was to transform cosmology from a discipline focused primarily on the past to one equally concerned with the future and with the fundamental nature of space itself. And in that transformation, the question of where the universe ends became more complex, more nuanced, and ultimately more fascinating than it had been when we thought expansion was simply slowing down. The discovery of cosmic acceleration sent echoes through time, affecting not just contemporary science but our entire conception of cosmic history and future. It revealed that the universe passes through different epochs, each dominated by different forces and characterized by different expansion rates. Understanding these epochs helps us see where we fit in the grand narrative and what it means that we happen to exist at this particular moment in cosmic time. In the beginning, immediately after the Big Bang, radiation dominated. The universe was filled with intensely hot photons and relativistic particles, their energy density far exceeding that of matter. Space expanded rapidly during this epoch, driven by the radiation's pressure. As expansion continued and the universe cooled, wavelengths stretched and energy densities dropped, but radiation remained dominant for the first tens of thousands of years. Then came the transition to matter domination. As the universe cooled and expanded, matter's density decreased more slowly than radiation's. Eventually, matter took over as the dominant component, and the expansion rate began to slow more noticeably under matter's gravitational influence. This epoch lasted billions of years, encompassing the formation of the first stars, the assembly of galaxies, and the growth of cosmic structure. It was during matter domination that the universe developed the complexity we see around us. But matter domination didn't last forever. As the universe continued to expand, matter became increasingly diluted, spread across larger and larger volumes. Dark energy, by contrast, maintained constant density as space grew, because it's a property of space itself, rather than objects within space. Eventually, about 5 or 6 billion years ago, dark energy's density exceeded matter's, and the universe entered its current epoch of dark energy domination. The expansion began to accelerate, and that acceleration has continued ever since. The echoes through time show us that the universe has evolved, not just in the structures it contains, but in the fundamental dynamics of its expansion. The forces shaping cosmic evolution have changed, and will change again in the future. The fact that we exist during the transition from matter to dark energy domination isn't coincidence. Complex structures like galaxies, stars, and planets can only form during matter domination, when gravity can overcome expansion to pull matter together. By the time dark energy takes over, the structures that will ever form have largely already formed. This timing has deep implications. If the universe were younger, still in the radiation-dominated era, no stable atoms would exist, let alone stars or galaxies. If it were much older, deep into dark energy domination, the expansion would have carried galaxies so far apart that any observers would see a sparse, dark universe with little evidence of its rich past. We exist in a narrow window, cosmologically speaking, when the universe is old enough for complexity but young enough to retain evidence of its origins. The impact of this realization affected how scientists think about anthropic reasoning, the idea that some features of the universe might be the way they are because only such features allow observers to exist. Dark energy's dominance couldn't have occurred much earlier, or the structures necessary for life wouldn't have had time to form. It couldn't have been much stronger, or expansion would have prevented structures from forming at all. The value of dark energy's density seems calibrated, whether by chance or by deeper physical principles we don't understand, to allow for a universe that can support complexity during a particular era. The echoes also resound in how we interpret observations. When we look at distant galaxies, we're seeing them during earlier epochs, when matter dominated and dark energy hadn't yet taken over. The universe behaved differently then. The expansion rate was slower. Structures formed more readily. By studying galaxies at different distances, we're essentially sampling different eras of cosmic history, watching the transition from matter to dark energy domination unfold across space and time. This has practical consequences for how we measure cosmic distances and expansion rates. The relationship between redshift and distance isn't simple when the expansion rate has changed over time. We have to account for which epoch we're observing, integrate the expansion history to determine how far light has traveled, and be careful not to assume that patterns we see nearby hold at extreme distances. The echoes of past epochs complicate measurements, but also enrich them, providing windows into the universe's evolution that wouldn't exist in a static or uniformly expanding cosmos. The impact extends to our understanding of the cosmic future. If dark energy remains constant, as observations suggest, then the universe will continue accelerating forever. The expansion rate will approach an asymptotic maximum, and space will grow exponentially, doubling in size at regular intervals. This de Sitter phase, named after the physicist who first described such solutions to Einstein's equations, will become the universe's final state, lasting eternally while becoming progressively emptier and darker. In this far future, the echoes of our epoch will fade. The galaxies we can see now will have long since crossed beyond the horizon. The stars will have burned out. Black holes will have evaporated through Hawking radiation. Even the protons that make up ordinary matter might decay, though this hasn't been observed and remains theoretical. Eventually, only the faintest quantum fluctuations will disturb the emptiness, and the universe will have reached something close to its maximum possible entropy. But those future epochs, bleak as they sound, are still part of the continuous story that the discovery of acceleration helped complete. The universe isn't static. It evolves through phases, each with its own character. The echoes we detect now, the subtle patterns in the cosmic microwave background, the distribution of galaxies, the light curves of distant supernovae, all tell us about the transitions between epochs, about how the balance of forces has shifted over time. The impact of understanding these echoes also changed how cosmologists think about other possible universes. If our universe passes through different epochs, then presumably other universes, if they exist, might have different transition timings, different balances between matter, radiation, and dark energy. Some might never develop structures, others might remain matter-dominated indefinitely. The fact that we observe particular transition times and particular densities suggests either that the physical constants are fine-tuned or that there's a selection effect, that we necessarily exist in a universe with properties that allow for observers during some epoch. The echoes through time also remind us of contingency. The universe didn't have to evolve the way it did. If the initial conditions had been slightly different, if quantum fluctuations in the early universe had different amplitudes, if dark energy had a different density, the history would have unfolded differently. The structures we see, the galaxies and stars and planets, exist because conditions happen to allow them to form during the matter-dominated epoch. Change those conditions even slightly, and the universe might have remained smooth and featureless, or might have collapsed before structures could grow. This contingency adds poignancy to our existence. We're here not just because the universe is large and old, but because we exist during a particular phase of its evolution, a phase that won't last forever in cosmic terms. The window during which observers can study a universe rich with structure and evidence of its history is narrow. Before that window, the universe was too young and simple. After it closes, the universe will be too old and empty. We happen to be looking out while the view is still good. The impact of these echoes also touches on the nature of scientific knowledge itself. We learn about cosmic history not by watching it unfold, which would take billions of years, but by interpreting patterns in the evidence available now. The echoes through time are written in light, in the distribution of matter, in the background radiation. Reading those echoes requires sophisticated instruments and careful analysis, but it works. We can reconstruct billions of years of history from observations made over decades, connecting the dots between different epochs to build a coherent narrative. And that narrative, with its transitions and epochs and evolving expansion rates, gives depth to the question of where the universe ends. The answer changes depending on which epoch you're in. During radiation domination, the observable universe was smaller and younger. During matter domination, it grew steadily. During dark energy domination, it will eventually stop growing as galaxies accelerate beyond the horizon. The edge of the universe isn't fixed. It's dynamic, responding to the forces that shape cosmic evolution, echoing the changes that have unfolded since the beginning and will continue until whatever counts as an end. Behind every cosmic discovery, behind every measurement and calculation, stand human beings driven by curiosity. The question of where the universe ends hasn't been pursued by abstract forces or impersonal institutions, but by individuals who devoted their lives to understanding something they could never fully see. These dreamers, astronomers, and physicists and theorists shaped our knowledge not just through their findings but through their persistence, their willingness to spend decades chasing answers that might never come. Edwin Hubble is perhaps the most celebrated of these dreamers, the man whose name became synonymous with cosmic expansion. But Hubble didn't work alone, and his discoveries built on the work of others who came before. Henrietta Leavitt, working at Harvard Observatory in the early 20th century, discovered the relationship between Cepheid variable periods and brightness that made distance measurements possible. She never received the recognition she deserved during her lifetime, but without her patient cataloguing of thousands of stars, Hubble couldn't have measured the distance to Andromeda or discovered the expansion of the universe. Vera Rubin spent decades studying galaxy rotation curves, work that required countless cold nights at telescopes, measuring the speeds of stars in galaxy after galaxy. Her data revealed the presence of dark matter, showing that the visible universe was embedded in something invisible and vast. She faced skepticism and resistance, both to her findings and to her presence as a woman in a field dominated by men. But she persisted, driven by curiosity about how galaxies really worked, and her observations fundamentally changed cosmology. These individuals weren't superhuman. They were people who chose to spend their finite lives pursuing questions that extended far beyond any single lifetime. They worked with imperfect instruments, incomplete theories, and limited resources. They made mistakes, followed false leads, and sometimes spent years on research that led nowhere. But they kept going, motivated by something deeper than career advancement or recognition. They wanted to know. They wanted to understand. They wanted to see what no one had seen before. The human element in cosmology is easy to overlook when we focus on discoveries and data. But every number in a catalogue represents hours of observation. Every theory represents years of thought. Every measurement represents a human being sitting at a telescope or computer, translating light into knowledge, bit by painstaking bit. The question of where the universe ends has been pursued by generations of such people, each one building on the work of predecessors, each one contributing small pieces to a picture that remains incomplete. Some of these dreamers never saw their work vindicated. Fritz Zwicky proposed the existence of dark matter in the 1930s based on observations of galaxy clusters. But his ideas were largely ignored during his lifetime. Albert Einstein formulated the equations that predicted cosmic expansion, but initially rejected that prediction, adding the cosmological constant to keep the universe static. He later abandoned it, only to have dark energy resurrect the concept decades after his death. The path from idea to acceptance is often long and winding, and not everyone who plants seeds lives to see the harvest. The dreamers came from many backgrounds and brought different perspectives to the same questions. Some were observers, happiest at the telescope capturing light from distant objects. Others were theorists, more comfortable with equations than instruments, exploring what mathematics said about cosmic possibilities. Still others were instrument builders, engineers who designed and constructed the telescopes and detectors that made new observations possible. All were necessary. All contributed to the collective effort. What united them was a particular kind of courage, the willingness to ask questions that seemed unanswerable. To wonder about the universe's extent requires accepting that you might never know the answer, that your life's work might be a small step toward understanding rather than a complete solution. It requires comfort with uncertainty, with provisional knowledge, with the possibility that everything you think you understand might be overturned by the next observation. The human element also includes failure and frustration. Instruments break, weather ruins, observing runs, funding disappears. Calculations contain errors that take months to find. Theories predict phenomena that observations don't confirm. The path to understanding is littered with setbacks, and only persistence allows progress. The dreamers who advanced cosmology weren't necessarily more brilliant than others, though many were certainly brilliant. But they were persistent, unwilling to give up when faced with difficulties. There's also the human cost of such pursuit. Astronomy requires long nights at remote observatories, time away from families, schedules that don't align with normal life. Theoretical work demands intense concentration, often solitary, wrestling with problems that resist solution. The competition for telescope time, funding, and academic positions creates pressure and stress. Many who begin with dreams of understanding the cosmos end up doing something else, worn down by the demands or discouraged by the slow pace of progress. But for those who stay, there's a reward that transcends conventional success. They become part of something larger than themselves, a collective human effort to understand reality that stretches across centuries. Every observation they make, every paper they publish, every student they teach, becomes part of the ongoing conversation humanity has with the cosmos. Their individual contributions might be small, but they're part of a pattern that accumulates into genuine understanding. The dreamers also share moments of profound experience that non-astronomers rarely encounter. To spend a night at a telescope, watching light arrive from galaxies billions of light years away, creates an almost visceral connection to cosmic scale. To solve an equation and realize it predicts something about the universe's structure creates a rush of recognition, a sense that mathematics and reality are somehow aligned. To see data confirm a prediction or contradict it and force new thinking is to feel the texture of reality pushing back against human ideas. These experiences shape the dreamers in ways that affect more than just their science. Many astronomers speak about feeling both smaller and larger when contemplating the cosmos, diminished by scale but elevated by comprehension. The question of where the universe ends becomes personal, not just because it's their research topic, but because wrestling with it changes how they see their own existence. You can't spend decades studying infinity without it affecting your perspective on your finite life. The human element includes serendipity too. Discoveries often come from unexpected directions. Arno Penzias and Robert Wilson weren't looking for the cosmic microwave background when they detected it. They were just trying to eliminate noise from a radio antenna. The discovery of cosmic acceleration came from astronomers measuring distant supernovae to refine the expansion rate, not expecting to find acceleration at all. Sometimes the universe reveals its secrets to those who aren't specifically asking the right questions, but are paying careful attention to what they observe. There's also collaboration, which has become increasingly important as instruments and analyses grow more complex. Modern cosmology involves teams of dozens or hundreds of researchers working together, each contributing expertise the others lack. The lone genius working in isolation is more myth than reality now. The dreamers of our era succeed through cooperation, building instruments together, sharing data, debating interpretations, and gradually converging on understanding through collective effort. The personal stories of these dreamers remind us that science is a human activity, subject to the same emotions, biases, and limitations as any other human endeavor. Scientists have egos, ambitions, prejudices. They compete for credit, argue over interpretations, sometimes resist ideas that threaten their own work. The progress of science isn't smooth or purely logical. It's messy, contentious, occasionally bitter. But it works, gradually and imperfectly, because the universe provides a reality check. Wrong ideas eventually fail when confronted with observation. What makes someone become a dreamer who pursues cosmic questions? Often it starts young, with a child looking up at the night sky and wondering what those lights are, how far away they might be, whether they go on forever. That sense of wonder, if it survives education and maturity, can develop into a driving force. Not everyone who wonders becomes a cosmologist, but every cosmologist began by wondering. The human element also includes sacrifice of a particular kind. To study the universe means accepting that most of what you want to know, you'll never learn. The dreamers work on problems that extend far beyond their lifespans, knowing that their contributions will be partial, that others will have to continue the work, that the full answer might never come. It takes a certain temperament to find satisfaction in incomplete knowledge, to celebrate small advances while recognizing how much remains unknown. And yet, despite the limitations and frustrations, despite the knowledge that the universe might be fundamentally unknowable in its full extent, the dreamers continue. New generations join the effort, bringing fresh perspectives and new technologies. The question of where the universe ends remains as compelling now as it was when humans first looked up and wondered about the lights above them. The dreamers who pursue it today stand on the shoulders of those who came before, and they're preparing the ground for those who'll come after. The human element ultimately reminds us that cosmology isn't just about the universe. It's about us, about what it means to be conscious beings in a cosmos we didn't create and can't fully grasp. The dreamers who study where the universe ends are really studying the boundary between knowledge and mystery, between what we can understand and what exceeds our understanding. And in that study, they find not just facts about galaxies and expansion rates, but something deeper. A sense of connection to the whole, a participation in the universe's ongoing attempt to know itself. Science advances not through consensus, but through conflict, through ideas tested against evidence and each other, until only the most robust survive. The question of where the universe ends has been marked throughout its history by opposition, by scientists who questioned prevailing views, who proposed alternatives, who demanded better evidence before accepting extraordinary claims. This opposition isn't obstruction, it's how science works, how truth emerges from the clash of competing interpretations. When Edwin Hubble first presented evidence for cosmic expansion, many astronomers resisted. The idea that the universe was growing contradicted centuries of assumption about an eternal, unchanging cosmos. Some proposed that light simply got tired over vast distances, losing energy and redshifting without any actual expansion. This tired light hypothesis was eventually ruled out by observations, but it represented a legitimate attempt to explain the data without requiring such a radical revision of cosmology. The opposition to new ideas serves an important function. It forces proponents to strengthen their arguments, to gather more evidence, to address alternative explanations. When scientists proposed that dark matter existed based on galaxy rotation curves, skeptics rightly demanded that other possibilities be explored first. Perhaps the observations were wrong. Perhaps our understanding of gravity needed modification on galactic scales, rather than invoking invisible matter. These alternatives had to be tested and eliminated before dark matter gained broad acceptance. The steady-state theory, proposed in the 1940s, represented sustained opposition to the Big Bang model. Its proponents argued that the universe had no beginning, that it looked the same at all times, with new matter continuously created to maintain constant density as space expanded. This avoided the uncomfortable implication of a cosmic origin, which some felt was too close to religious creation stories. The debate between Big Bang and steady-state cosmology was fierce, sometimes personal, lasting decades. The discovery of the cosmic microwave background in 1965 effectively ended that debate, providing evidence for a hot early state that the steady-state theory couldn't explain. But the opposition served its purpose. It forced Big Bang proponents to make testable predictions, to specify exactly what observations would confirm or refute their model. The competition between theories strengthened both sides' arguments and ultimately led to clearer understanding. Opposition also comes from limitations in measurement. When Type Ia supernovae data first suggested cosmic acceleration, many astronomers were skeptical. The measurements were at the edge of what was possible. The uncertainties were large. Perhaps systematic errors were mimicking acceleration. Perhaps distant supernovae were intrinsically different from nearby ones in ways not accounted for. These concerns were valid and forced the teams making the measurements to work harder, to find independent confirmation. to rule out alternative explanations. The battle for truth about cosmic acceleration lasted several years before acceptance became widespread. Multiple independent observations had to converge on the same conclusion. The cosmic microwave background had to show patterns consistent with dark energy. Large scale structure surveys had to match predictions of accelerating expansion. Only when all these different lines of evidence pointed the same direction did the opposition gradually fade. But opposition doesn't always disappear completely. Even today, some scientists question whether we truly understand dark energy, whether there might be alternative explanations for cosmic acceleration that don't require mysterious vacuum energy. Modified gravity theories propose that Einstein's equations need adjustment on cosmic scales. These alternatives are explored, tested against observations, and largely ruled out, but the process continues. The opposition keeps the mainstream theory honest, prevents complacency, ensures that no possibility is dismissed without careful examination. The battle for truth also involves methodological disputes. How do you measure distances to galaxies? Which techniques are most reliable? How do you account for systematic errors? Different research groups sometimes get different results using different methods, and resolving those discrepancies can take years. The opposition between competing techniques and analyses forces refinement, standardization, cross-checking that strengthens the final conclusions. There's also philosophical opposition. Scientists uncomfortable with the implications of certain findings. The idea that most of the universe is invisible and unknown bothers some who prefer cosmology to deal only with what can be directly observed. The notion that we'll never see beyond the cosmic horizon, never know whether the universe is infinite or finite, troubles those who believe science should eventually answer every question. This philosophical discomfort motivates searches for ways around the limitations, for indirect methods of probing the unobservable, for loopholes in the apparent impossibility of certain knowledge. The opposition sometimes comes from outside science entirely. Religious groups occasionally object to cosmological findings that seem to conflict with creation narratives. Philosophers question whether cosmology's methods are truly scientific when they involve one-time events that can't be repeated or tested experimentally. Popular writers sometimes promote fringe theories that contradict mainstream cosmology, finding audiences receptive to alternatives that challenge expert consensus. Dealing with this external opposition requires different skills than handling scientific disagreement. Scientists must learn to communicate not just with each other but with the public, explaining why certain ideas are accepted and others rejected, what constitutes good evidence, how scientific consensus develops. This outreach is important but time-consuming, taking effort away from research itself. The battle for truth also involves competition for resources. Telescope time is limited. Funding is scarce. Research groups compete to be the first to make discoveries, to publish results, to attract talented students. This competition can be healthy, spurring innovation and efficiency. But it can also create pressure to over-interpret data, to claim discoveries prematurely, to downplay uncertainties. The opposition between competing groups sometimes becomes personal, affecting careers and reputations. Peer review provides a formal mechanism for opposition within science. Every paper submitted to a journal is scrutinized by other experts who look for errors, question assumptions, and demand that claims be supported by evidence. This process can be brutal, with reviewers sometimes rejecting work that later proves correct. But it serves as a filter, catching mistakes and forcing authors to improve their arguments. The opposition of peer review, frustrating as it can be, maintains standards and credibility. Historical cases show both the value and the danger of opposition. Continental drift proposed by Alfred Wegener in the early 20th century, faced fierce opposition for decades before being accepted as plate tectonics. The opposition delayed acceptance of a correct idea, but also motivated the gathering of evidence that eventually made the case overwhelming. On the other hand, some opposition has simply been wrong, resistance based on prejudice or misunderstanding rather than legitimate scientific concerns. The battle for truth about where the universe ends continues today. Some researchers argue that the observable universe's apparent flatness and homogeneity are illusions, that we happen to live in an unusual region of a larger, more varied cosmos. Others propose that our universe is one bubble in an eternal inflation scenario, with countless other universes beyond our horizon. These ideas face opposition from those who insist cosmology should stick to what's observable, that speculation about unobservable regions isn't science. This debate touches on fundamental questions about the nature of scientific knowledge. Can we make scientific claims about regions we can never observe? Is a theory scientific if its predictions can't be tested? Different scientists answer differently, and the opposition between these viewpoints shapes what research gets pursued and what gets dismissed as philosophy rather than physics. The battle also involves interpretation of data. The same observations can sometimes support different models. The cosmic microwave background's patterns constrain, but don't uniquely determine the universe's properties. Different theoretical frameworks can fit the data equally well, at least within current measurement uncertainties. Choosing between them requires additional evidence or philosophical preferences, and reasonable scientists can disagree about which approach is most promising. Opposition also comes from the recognition that our theories are incomplete. General relativity and quantum mechanics, the two pillars of modern physics, are incompatible in certain situations. At the Planck scale, where quantum effects become important for gravity, neither theory works properly. This incompleteness means that our cosmological models, based on these theories, might be wrong in fundamental ways we haven't recognized. Some opposition stems from this awareness, a healthy skepticism about extrapolating theories beyond their proven domains. The battle for truth requires humility as well as confidence. Scientists must be confident enough to propose new ideas, to challenge accepted views, to pursue research directions others dismiss. But they must also be humble enough to change their minds when evidence demands it, to acknowledge when they're wrong, to recognize the limits of their knowledge. The tension between these attitudes creates the dynamic opposition that drives science forward. In the end, the opposition serves truth rather than obstructing it. Ideas that can't withstand scrutiny don't deserve acceptance. Questions without good answers shouldn't be declared solved. Mysteries that remain mysterious need to be acknowledged rather than hidden behind false certainty. The battle for truth about where the universe ends is ongoing precisely because the truth is difficult, the evidence incomplete, and the implications profound. And in that ongoing battle, both sides, those proposing new ideas and those questioning them, contribute to the gradual accumulation of genuine understanding. There comes a moment in the pursuit of knowledge when pieces that seemed separate suddenly connect, when scattered observations coalesce into a pattern, when understanding shifts from fragmented to coherent. For cosmology, this awakening came gradually through the late 20th and early 21st centuries, as multiple lines of evidence converged to reveal a consistent picture of the universe's nature, structure, and fate. It was a collective realization that transformed not just what we knew, but how we understood our cosmic situation. The awakening began with the recognition that the universe had a story, a narrative arc from beginning to present to future. This might seem obvious now, but for most of human history, the cosmos was thought to be eternal and essentially unchanging. The discovery of expansion revealed that the universe evolved, that it had been different in the past and would be different in the future. This narrative structure gave meaning to observations that might otherwise have seemed like isolated facts. Different observations started fitting together like pieces of a puzzle. The cosmic microwave background showed the universe as it was roughly 380,000 years after the Big Bang, a time when matter and radiation decoupled and light could travel freely. Galaxy surveys showed how matter had clumped together under gravity's influence over billions of years. Supernova observations revealed how the expansion rate had changed over cosmic history. Each piece of evidence told part of the story, and together they formed a coherent whole. The awakening included understanding that the universe had gone through distinct phases. The radiation-dominated era, when photons and relativistic particles controlled cosmic dynamics. The matter-dominated era, when gravity pulling on cold matter shaped the formation of structure. The dark energy-dominated era, when mysterious vacuum energy began driving accelerated expansion. These weren't arbitrary divisions, but genuine transitions when different components became dominant and the universe's behavior fundamentally changed. This phase structure helped explain why we see what we see. Galaxies formed during matter domination because that's when gravity could overcome expansion to pull matter together. The cosmic microwave background exists because the universe was once hot enough to ionize all atoms, then cooled enough for electrons and nuclei to combine, releasing a flash of light that's been traveling ever since. Dark energy only recently took over because its density stayed constant while matter's density decreased as the universe expanded. The awakening also involved recognizing patterns across scales. The same physics that describes how planets orbit stars also describes how stars orbit galaxies. The same quantum fluctuations that create uncertainty in particle positions also seeded the density variations that grew into galaxies. The same expansion that carries distant galaxies away from us is happening everywhere in the universe. Not because we're at the center, but because space itself is growing uniformly. This scale invariance of physical law was itself a crucial realization. The universe operates according to consistent principles whether you're looking at atoms or galaxy clusters. There's no point where the rules suddenly change, no boundary where different physics applies. This uniformity allows us to extrapolate from what we observe nearby to conditions in distant regions and ancient times. It's what makes cosmology as a science possible. The awakening included accepting that we live in a special time, cosmologically speaking, not special in the sense that the universe has singled us out, but special in that we happen to exist during an era when the cosmos is particularly interesting and observable. Earlier, there were no stable structures, no stars or planets. Later, expansion will have carried most galaxies beyond our horizon, leaving a dark, sparse universe. We're here during the window when conditions allow both for life and for studying the universe's full history. This temporal perspective changed how scientists thought about observation and knowledge. What we can see isn't fixed but depends on when we're looking. Future astronomers, assuming any exist trillions of years hence, will have less cosmic evidence available than we do. They'll observe a smaller universe with fewer galaxies and dimmer background radiation. The window of observability opens and closes, and we happen to be looking through it during one of its most revealing moments. The awakening also involved understanding the deep connection between observation and existence. We can only observe the universe by being part of it, by using atoms and light that follow the same physical laws as everything else. There's no outside perspective, no way to step back and view the cosmos objectively. Every observation is made from within. colored by our location in space and time, limited by the finite speed of light and the finite age of the universe. This self-referential quality, far from being a limitation, became recognized as fundamental to cosmology. We're not external observers studying an object separate from ourselves. We're the universe observing itself, matter arranged in a configuration that can contemplate its own existence. That awareness, that capacity for self-reflection, might be the universe's rarest and most remarkable feature. The awakening included reconciling the very large with the very small. Cosmology and particle physics, once separate disciplines, merged as scientists realized they were studying the same thing from different angles. The early universe was hot and dense enough that particle physics mattered. The formation of elements in the Big Bang depended on nuclear physics. The quantum fluctuations that seeded galaxies connected the smallest and largest scales. Understanding the universe required understanding both extremes and how they influenced each other. This unification of scales revealed deep connections. The atoms in our bodies were forged in stellar furnaces billions of years ago. The light we see from distant galaxies began its journey before Earth existed. The expansion that carries galaxies apart also affects the space between atoms. Though local forces easily overcome it, there's no separation between the cosmic and the personal. They're part of the same continuous fabric of existence. The awakening also meant accepting uncertainty as fundamental rather than temporary. Some aspects of the universe aren't just currently unknown, but potentially unknowable. The region beyond our cosmic horizon can't send us information. The initial conditions of the Big Bang might be forever obscured by the chaotic dynamics of the earliest moments. The true extent of the universe, whether infinite or finite, might remain permanently ambiguous. This wasn't failure, but a recognition of built-in limits to knowledge. With that recognition came a different kind of humility. Not the humility of ignorance, but the humility of knowing what can and can't be known, of understanding that some mysteries aren't puzzles to be solved, but permanent features of our cosmic situation. The awakening involved making peace with this, finding satisfaction in partial knowledge, accepting that the universe is under no obligation to be fully comprehensible. The new awareness also changed how scientists communicated with the public. Instead of presenting cosmology as a completed body of facts, they began emphasizing the ongoing nature of the quest, the open questions, the provisional nature of current understanding. This honesty about uncertainty, far from undermining science's credibility, strengthened it by showing that science was a process of discovery rather than a collection of dogmas. Public fascination with cosmology grew as the awakening spread beyond specialists. People responded to the narrative of cosmic evolution, to the idea that the universe had a history and a future, that we were part of something larger and stranger than everyday experience suggested. The questions that cosmology addressed — where do we come from? How did everything begin? Where is it all going? — resonated with deep human concerns, even when expressed in mathematical and observational terms. The awakening also transformed how we think about edges and boundaries. The universe might not have a spatial edge, but it has temporal boundaries, a beginning at the Big Bang, and potentially different kinds of endings in various far future scenarios. It has observational boundaries, horizons beyond which we can't see. It has conceptual boundaries, limits to what we can understand with current physics. These different kinds of edges replace the simple notion of a spatial boundary, where space just stops. Understanding came to be seen not as reaching a final answer, but as deepening engagement with mystery. Each discovery opened new questions. Each answer revealed more of what we didn't know. The awakening was recognizing that this pattern would continue indefinitely, that the pursuit of understanding where the universe ends was really a pursuit of continually refined questions rather than ultimate answers. And perhaps most importantly, the awakening involved seeing ourselves differently, not as isolated beings on a small planet, but as participants in cosmic evolution, temporary configurations of matter capable of understanding, however partially, the system that produced us. The question of where the universe ends became inseparable from the question of what it means to be conscious within that universe, to be the part of reality that can ask about the whole. This new awareness didn't provide final answers, but it offered something more valuable, a framework for thinking about our cosmic situation, a way of understanding how different pieces of evidence fit together, a narrative that connected the very beginning to the distant future. The awakening was realizing that we were part of a story still being written, that our observations contributed to the universe's gradual self-understanding, and that the edges we sought weren't boundaries to cross, but perspectives to shift. After all the observations and calculations, after decades of mapping galaxies and measuring expansion rates, after theoretical breakthroughs and technological advances, cosmology arrives at a revelation that's both simple and profound. The universe, as far as we can determine, doesn't have an edge in the way we intuitively imagine edges. There's no wall where space stops, no boundary you could reach by travelling far enough. The end of the universe isn't a place, it's a limit of observation, a horizon defined not by the cosmos itself, but by our ability to gather information from it. This revelation emerges from combining what we know about cosmic expansion, the finite speed of light, and the finite age of the universe. Space has been expanding for roughly 13.8 billion years. Light travels at a fixed speed, about 300,000 kilometers per second. These two facts together determine how far we can see. Light from regions more distant than about 46 billion light-years hasn't had time to reach us yet. That distance marks the edge of the observable universe, the cosmic horizon beyond which we cannot see. But here's the crucial point. That horizon isn't a property of space itself. It's a property of observation. It's where light's reach ends, not where the universe ends. Beyond that horizon, space presumably continues, following the same physical laws, containing more galaxies and stars and structures. We can't see them, not because they're different or special, but simply because their light hasn't had time to traverse the expanding space between us and them. The deepest truth is that the observable universe is almost certainly much smaller than the actual universe. How much smaller, we can't say. The universe beyond our horizon might be 10 times larger than what we can see. It might be 1,000 times larger. It might even be infinite. We have no way to measure it directly. No observation we could make that would definitively tell us the total extent of space. The cosmic horizon is absolute, a boundary we can never cross through observation, no matter how long we wait or how powerful our telescopes become. This limitation isn't temporary or technological. It's built into the structure of space-time itself. Information can't travel faster than light, and space is expanding such that distant regions recede faster than light can cross them. With cosmic acceleration driven by dark energy, this horizon has become fixed. Galaxies beyond it are receding so fast that their light will never reach us, even given infinite time. They're causally disconnected, forever beyond our ability to interact with or observe. The revelation extends deeper still. Not only can we never see the whole universe, we can't even be certain about its basic properties. Is space flat and infinite, or does it curve back on itself into a closed, finite volume? Current measurements show flatness to within a small margin of error, but that margin leaves room for either possibility. The universe could extend infinitely in all directions, or it could be finite, but so large that its curvature is too subtle for us to detect. Both possibilities are consistent with observation. Both fit within the framework of general relativity. Both predict much the same patterns in the cosmic microwave background and the distribution of galaxies. We can't distinguish between them using current or foreseeable measurements. The deepest truth about the universe's extent might be permanently beyond our reach. Not because we lack cleverness, but because the information simply isn't accessible from our position within space-time. This revelation has philosophical weight. We're used to thinking that sufficiently determined investigation will eventually reveal any truth, build a better telescope, develop a more sensitive detector, wait long enough, and eventually we'll see what we need to see. But cosmology has revealed fundamental limits to that optimism. Some truths about the universe might be forever unknowable. Not temporarily, but permanently. Not practically, but in principle. The deepest truth also involves accepting that our perspective is necessarily limited. We observe the universe from one location in space, one moment in time. We can't step outside to see it from different angles. We can't rewind time to watch how structures formed, or fast forward to see how they'll evolve. We're embedded within what we study, using tools and minds that are themselves products of cosmic evolution. Our knowledge is always from within, always partial, always constrained by our situation. Yet within those constraints, we've achieved remarkable understanding. We've traced the universe's history from fractions of a second after the Big Bang to the present. We've measured its expansion rate, its composition, its large-scale structure. We've identified the major forces shaping cosmic evolution and made predictions about its future. The fact that some questions remain unanswerable doesn't diminish what we have learned. It just reminds us that reality is deeper than any description of it. The revelation also concerns the relationship between the observable and the actual. What we can see is a tiny fraction of what exists. The observable universe contains perhaps 2 trillion galaxies, each with hundreds of billions of stars. That's an almost inconceivable amount of matter and space. Yet if the universe is infinite, or even just very large, the observable portion might be negligible compared to the whole. We're like people on a raft in the middle of the ocean, able to see to the horizon in all directions, but unable to determine how far the ocean extends beyond our view. This perspective changes what we mean by the universe. In common usage, universe means everything that exists. But in cosmology, we often mean the observable universe, the portion we can access through light and other signals. The distinction matters because the actual universe might be far larger, far stranger, or far more varied than what we observe. Our theories and models describe what we can see, but their applicability to regions beyond observation remains uncertain. The deepest truth includes recognizing that dark matter and dark energy, which together comprise 95% of the universe's content, remain essentially mysterious. We know they exist through their gravitational effects, but we don't know what they fundamentally are. The visible matter, stars and gas and dust, is only the tip of an enormous iceberg. Most of the universe, even the part we can observe, is invisible and poorly understood. The edge of knowledge runs through the middle of what we can see, not just at the distant horizon. There's also a temporal dimension to this revelation. We can observe the past by looking at distant objects whose light began its journey billions of years ago. But we can't observe the present state of those objects. We see them as they were, not as they are. The farther we look, the further back in time we see, until we reach the cosmic microwave background, the oldest light observable. Beyond that lies the opaque early universe, forever hidden from direct observation. The edge of the observable universe is really an edge in time, as much as space. The revelation brings us back to the original question with a new understanding. Where does the universe end? The observable universe ends at the cosmic horizon, where light's reach expires. But the actual universe, the full extent of space and everything it contains, either extends infinitely or ends in a way we cannot observe or specify. The question has no single answer because it conflates two different things: the edge of observation and the edge of existence. The first is well defined. The second might not exist at all. This ambiguity isn't a failure of science, but a feature of reality. The universe is under no obligation to make itself fully knowable. It exists according to its own nature, following physical laws that govern both what we can see and what we can't. Our ability to observe is limited, but the universe's extent is not necessarily limited in the same way. There's a boundary to knowledge that doesn't correspond to any boundary in space. The deepest truth is that we must live with this ambiguity, neither despairing of our limitations nor pretending they don't exist. We can study what's observable, build models that fit the data, make predictions about what we'd see if we could look farther. But we must also acknowledge that some aspects of the cosmos remain and might always remain beyond our reach. The universe keeps its secrets not out of cruelty, but simply because information can't travel infinitely fast across expanding space. And perhaps there's something appropriate about that. The question of where the universe ends, when pursued seriously and scientifically, leads not to a definite answer, but to a deeper appreciation of both cosmic vastness and human limitations. It teaches humility without destroying wonder. It shows us the boundaries of the knowable without diminishing the value of what we've learned within those boundaries. The revelation is that the edge we seek isn't a place we can reach or even precisely define. It's a horizon that marks the limit of light's journey, a boundary between what can be known and what must remain mysterious. And in accepting that boundary, in making peace with permanent uncertainty about the universe's full extent, we find a kind of wisdom. Not the wisdom of complete knowledge, but the wisdom of knowing what can be known and being at peace with what can't. When you step back from the observations and equations, from the measurements and theories, and simply reflect on what cosmology has revealed about the universe's extent, a certain pattern emerges. The question of where the universe ends has guided us not to a simple answer, but to a deeper understanding of both the cosmos and ourselves. What began as a straightforward inquiry, a child's question about boundaries, has unfolded into something far more subtle and profound. The meaning of the cosmic horizon, that boundary beyond which we cannot observe, extends beyond mere distance. It's a reminder that we exist within rather than above reality, that our perspective is necessarily limited, that knowledge itself has edges we cannot cross. This isn't a defect to be overcome through better technology. It's a fundamental feature of existence in a universe with a finite age and a finite speed for information transfer. There's something humbling in this realization. We've grown accustomed to thinking of human knowledge as potentially unlimited, that given enough time and effort, we can eventually understand anything. Some regions of the universe are forever beyond our reach, not temporarily but permanently. The expansion of space creates an absolute boundary to observation that no amount of ingenuity can circumvent. Yet there's also something liberating in accepting this limit. It frees us from the burden of needing to know everything, from the anxiety that our knowledge remains incomplete. Of course, our knowledge is incomplete. It must be. The universe has ensured through its own structure that complete knowledge is impossible. What matters isn't knowing everything, but understanding what we can know and being honest about what we can't. The reflection also touches on the nature of existence itself. We are finite beings contemplating infinity, temporary forms, thinking about eternity, small configurations of matter pondering the largest structure we can conceive. That paradox, that tension between our scale and the cosmos's scale, is part of what makes us human. We can imagine more than we can experience, think about more than we can see, understand concepts that extend far beyond our immediate reality. The universe's possible infinity, or vast finitude, has meaning for how we see ourselves. If space extends forever, then in some sense everything that can happen does happen somewhere. Every possible arrangement of matter, every variation on cosmic structure would exist in some distant region. This infinite diversity would make a particular corner less unique, but not less real or less valuable. Uniqueness isn't required for meaning. If the universe is finite, even if vastly larger than the observable portion, then there's a totality to existence, a whole that's vast but bounded. This creates a different kind of meaning, a sense that the universe is complete in itself, self-contained, not requiring anything external. Either way, infinite or finite, the cosmos is sufficient unto itself, following its own rules, existing without need for outside validation. The reflection also considers what it means that we happen to exist during an era when the universe is observable, when light from distant regions can still reach us, when the cosmic microwave background remains detectable, when galaxies haven't yet accelerated entirely beyond our horizon. This timing isn't random. Complex structures like stars, planets, and life can only form during certain cosmic epochs, when conditions are neither too hot and dense, nor too cold and sparse. We necessarily exist when observation is possible, because observation requires observers, and observers require conditions that also allow observation. This anthropic reasoning, while sometimes controversial, highlights a deep connection between existence and knowledge. The universe has to be a certain way for consciousness to arise, and that same way makes the universe knowable to that consciousness. We're not passive viewers of an unrelated cosmos, but participants in a system that has produced us and that we can partially understand precisely because we're part of it. The meaning of cosmology's findings about cosmic extent also relates to the nature of boundaries themselves. We've discovered that the universe doesn't have edges in the naive sense, no walls where space stops. Instead, it has horizons, observational limits, asymptotic approaches to knowledge rather than hard barriers. This pattern appears throughout physics. Many apparent boundaries turn out to be continuous transitions, smooth approaches to limits rather than discontinuous breaks. Perhaps this tells us something about reality's structure, that nature abhors true discontinuity, that the universe is fundamentally continuous even when it appears bounded. The cosmic horizon isn't a wall, but a distance beyond which information can't reach us. The Big Bang wasn't an explosion at a point, but an emergence of space and time from conditions we can barely describe. Even quantum mechanics, with its apparent jumps and uncertainties, might be continuous in ways we don't yet understand. The reflection includes thinking about the relationship between part and whole. We are parts of the universe studying the whole, but we can never see the whole from outside. Our knowledge is always that of one part examining others, inferring the whole from partial evidence. This is simultaneously a limitation and a testament to reason's power, that we can infer so much from so little, that we can extrapolate universal laws from local observations, shows that understanding doesn't require complete access. There's also meaning in the vastness itself. The observable universe contains more stars than grains of sand on Earth, more galaxies than humans who have ever lived, more space than could be travelled in billions of years at light speed. And that's just what we can see. The actual universe might be far larger still. This immensity isn't threatening, it's context. It shows us that whatever problems or concerns occupy our attention, they occur within something infinitely larger, something that existed long before us and will continue long after. This perspective can be either nihilistic, making everything seem pointless against cosmic scale, or liberating, freeing us from the burden of cosmic significance. The universe doesn't care about our concerns because it doesn't care about anything. It simply exists, following physical laws, evolving according to dynamics that predate and will outlast any observer. Our concerns are real to us, precisely because we're not cosmic. We're local, temporary, finite, and that's where meaning lives. The reflection also considers what future humans, if any exist, might learn about cosmic extent. With better instruments, they'll measure things more precisely, but they'll also face the same fundamental limits we do. The cosmic horizon isn't something technology can overcome. Future astronomers will know more than we do about the observable universe, but they won't know whether the full universe is infinite or finite. That question might remain forever unanswered, passed from generation to generation, not as a solvable problem but as a permanent mystery. Perhaps some questions are meant to remain open, not because they're unanswerable in practice, but because their openness is essential to human inquiry. The question of where the universe ends keeps us looking, measuring, thinking, reaching beyond what we know, toward what we don't. If we ever found a definitive answer, if we somehow determined that space is precisely this large, or extends exactly that far, would it end our curiosity, or just redirect it? The meaning we find in cosmology's revelations about cosmic extent is ultimately what we bring to them. The universe offers facts, patterns, evidence. We interpret those offerings, finding in them reflections of our own concerns and values. The edge of the universe, whether real or merely observational, mirrors our own edges, our limits of understanding and existence. In studying cosmic boundaries, we're also contemplating our own, but the reflection shouldn't end in abstraction. The question of where the universe ends has practical import too. It shapes how we allocate research resources, what observations we prioritize, what theories we develop. It affects how we communicate science to the public, what stories we tell about cosmic origins and fate. It influences how new generations think about their place in the cosmos, whether they see themselves as central or peripheral, significant or insignificant, connected or isolated. The deepest meaning might be that the question itself matters more than any answer. To ask where the universe ends is to assert that boundaries matter, that extent has significance, that the shape and size of existence are worth contemplating. It's to engage with reality at its largest scale, to think beyond the immediate and local, to practice the kind of abstract reasoning that might be humanity's most distinctive feature. And in that engagement, in that willingness to contemplate the incomprehensibly vast, we transcend our own smallness, not by becoming large ourselves, but by thinking thoughts that span cosmic distances, by understanding patterns that encompass billions of years, by connecting ourselves mentally to the whole of existence, even though we can only ever experience a tiny fraction of it. The reflection on cosmic extent is really a reflection on what it means to be conscious in a universe that vastly exceeds consciousness, to be the part that can wonder about the whole. As we come to the end of this gentle journey through the cosmos, through questions of edges and horizons and the ultimate extent of everything, it helps to return to where we began. The question of where the universe ends, asked in the dark before sleep, carries us outward through billions of light years and billions of years of time, through observations and theories, through human stories of discovery and wonder. And now, having travelled that distance, we can return home with a different understanding. The legacy of pursuing this question isn't a simple answer. We haven't found a wall at the edge of space or a sign saying universe ends here. Instead, we've discovered that the cosmos is stranger and more subtle than any simple boundary could capture. The universe, as far as we can tell, either extends infinitely in all directions or curves back on itself in ways that create finite volume without edges. Either way, it has no simple end, no place where space just stops. But we have found edges of another kind. The cosmic horizon marks the limit of observation, the distance beyond which light hasn't had time to reach us since the Big Bang. That boundary is real and measurable, about 46 billion light-years away in every direction. It defines the observable universe, the portion of the cosmos we can study and understand through light and other signals. Beyond that horizon lies mystery, regions that are real but forever unknowable through direct observation. The legacy also includes understanding that we live in a special time. Not special in the sense that the universe favours us, but special in that we exist during an era when observation is rich with evidence. The cosmic microwave background is still detectable. Distant galaxies are still visible. The history of cosmic expansion is still written in the light that reaches us. In the far future, when dark energy has carried most structures beyond the horizon, when background radiation has cooled into invisibility, future observers will have less to work with than we do. We're fortunate to be looking while the view is still good. This temporal perspective adds urgency to the scientific project. The evidence available now won't last forever. Observations made today contribute to a historical record that future generations will need because they won't be able to replicate those observations themselves. Cosmology has become not just a study of the present universe, but an act of preservation, capturing data about cosmic conditions that will eventually become inaccessible. The legacy of exploring cosmic extent also includes the human stories we've touched on throughout this journey. The astronomers who spent lifetimes measuring distances to galaxies, the theorists who developed frameworks for understanding expansion and acceleration, the instrument builders who created telescopes capable of seeing across billions of light years. Their work collectively forms a monument to human curiosity, to the drive to understand that seems to be one of our species' defining characteristics. These individuals won't be remembered like politicians or celebrities. Most of their names will fade from common knowledge within a generation or two of their deaths, but their contributions endure in a different way. Every cosmology textbook builds on their findings. Every new observation stands on the foundation they laid. The legacy isn't personal immortality, but collective achievement, the gradual accumulation of knowledge that transcends individual lifetimes. As we return from contemplating cosmic distances, we also return with a changed sense of scale. The problems that seemed large before, personal concerns and social issues, remain important. They matter to us because we're humans living human lives, and that's the scale where meaning lives. But they're now situated within a larger context, against a background of cosmic vastness that provides perspective without diminishing significance. The return journey also brings us back to the personal, to the experience of looking up at the night sky and feeling that mixture of wonder and smallness. The stars we see are nearby neighbours in cosmic terms, most within a few thousand light years. Yet even those relatively close objects are so far away that their light takes years to reach us. The farthest galaxies visible to our telescopes sent their light billions of years ago, when Earth was young or didn't yet exist. Every glance upward is a look backward through time, a direct connection to the ancient past. The legacy of cosmology's findings about where the universe ends is partly about knowledge, about facts and measurements and theories, but it's also about wonder, about maintaining the capacity to be astonished by reality, about staying open to the strangeness of existence. The universe doesn't stop being remarkable just because we understand it better. If anything, understanding deepens wonder by revealing layers of subtlety that naive amazement misses. The closing of this exploration doesn't mean the question is settled. Science continues. New observations refine our understanding, and future discoveries might reveal aspects of cosmic structure we haven't imagined. The question of where the universe ends will persist as long as humans look up and wonder, as long as we build instruments to extend our vision, as long as curiosity drives us to ask about boundaries and limits and ultimate extent. But for tonight, for this moment before sleep, we can let the question rest. We've followed it as far as current knowledge allows, through observations and evidence, through theories and implications, through the work of those who devoted their lives to cosmic understanding. We've seen that the universe, if it ends at all, ends beyond our ability to observe. The horizon we can measure is one of light and information, not necessarily of space itself. And in that realization, there's a kind of peace. The universe doesn't demand that we comprehend it fully. It exists whether we understand it or not, following its own laws, unfolding its own evolution. Our inability to see beyond the cosmic horizon doesn't make the universe less real or our knowledge less valuable. It simply means we're finite beings in a cosmos that might be infinite, local observers in a universe that extends beyond locality. The return to the immediate, to the room where you're listening, to the comfort of rest after a long journey through space and time, brings its own relief. The cosmic questions don't need to be answered tonight. They'll wait, patient as starlight, for the next moment of curiosity, the next clear night when someone looks up and wonders about boundaries. The legacy we carry back from this exploration is multi-layered. There's the factual knowledge. The observable universe is about 93 billion light-years across. The expansion is accelerating. Dark energy dominates cosmic dynamics. The horizon is both real and unreachable. There's the methodological understanding, how scientists measure distances, how they infer invisible matter's presence, how they reconstruct cosmic history from present evidence. There's the philosophical awareness that some questions might be permanently unanswerable, that knowledge has edges, that mystery is fundamental rather than temporary. But perhaps most importantly, the legacy includes a renewed sense of connection. The atoms in your body came from stars that died before the sun formed. The light touching your eyes right now began its journey from the sun 8 minutes ago. The ground beneath you is part of a planet orbiting through space at tremendous speed, carried along by the sun's motion around the galactic center, which is itself moving through intergalactic space. You're not separate from the cosmos. You're part of it, a temporary configuration of matter that can think and wonder and understand, however partially. As sleep approaches, as thoughts begin to drift, you can let the vastness recede. The universe will continue its expansion without your attention. Galaxies will keep moving apart. Stars will burn. Space will stretch. All of that happens, whether or not anyone observes it, whether or not anyone understands it. The cosmic drama proceeds independent of human consciousness, as it did for billions of years before we existed, and will for billions more after we're gone. But in this moment, consciousness and cosmos meet. The question of where the universe ends, pondered in the quiet before sleep, connects your finite awareness to the possibly infinite whole. It's a meeting point between the small and the large, the temporary and the eternal, the known and the unknowable. And in that meeting, in that gentle contemplation of cosmic extent, there's a recognition of belonging, a sense that however vast and strange the universe might be, you're part of it. The closing isn't really an ending. The question remains open, waiting for new evidence and new understanding. Science continues its patient accumulation of knowledge. The universe continues its expansion, and consciousness continues its improbable existence, looking out from small planets orbiting ordinary stars, asking questions about the whole, finding not final answers but ever deeper engagement with mystery. So, as we come to rest here, having travelled through space and time in thought if not in body, having contemplated horizons and boundaries and the ultimate extent of everything, we can let the question settle into silence, not because it's been answered, but because it's been honoured. We've given it the attention it deserves, followed it as far as we can go, and found that the journey matters more than the destination. Embrace. Every breath you take is part of its ongoing evolution. Every thought you think is the cosmos becoming aware of itself. And every moment of wonder, every question about boundaries and edges and ultimate limits is the universe exploring its own nature through you. Rest now. The stars will still be there tomorrow, still billions of years old, still billions of light years away. The question of where the universe ends will wait. And in the morning, when you wake to another day on this small planet in this vast cosmos, you'll carry with you a deeper understanding of the territory you inhabit, both the immediate and the infinite, both the known and the unknowable. The legacy is yours to keep, the knowledge and the wonder, the facts and the mystery. And perhaps that's the answer the question was always seeking. Not a location where the universe ends, but an understanding that extends your awareness to the cosmos's horizons, wherever and whatever they might be. Good night. Sleep well. The universe continues, and you within it, each part of the other, connected by the same fabric of existence that weaves through everything, from the smallest particle to the largest structure, from this moment to all time, from here to everywhere, without end,